All right. Good morning, everyone. We're getting underway. I've already done the introduction here for the people in the room for the housekeeping, so we can jump to the next slide. All right. All right. We are Cosmic, and this is the Cosmic Capstone Challenge. This is the final showcase, starting today and running through Thursday. My name is Jacob Rome. I've been managing C3 for the past several years, and let's roll. All right, next slide. Okay, so introduction, ground rules. We're excited to have you, whether you're online or in the room. It's really cool. If you need anything or have any questions, post in the Zoom chat, or you can reach out to myself, Alec, or Rachel. Rachel's also be very helpful and keep posting links in the Zoom. If you're attending in person, please be respectful during the other presentations, even if they're not in the room here. We should not be having conversations in this room. Next door here in El Segundo, there's an empty room if you want to do that. Okay, so there'll be a lot of people attending it eventually. We're going to limit it so the only presenters and judges may come off mute. So if you're an audience member and you have questions, put the questions in the chat. If you're a judge, you can come off mute and ask or raise your hand. Others are encouraged to post questions in the chat, and we're going to stay on schedule. Unfortunately, we had a couple teams drop out the last minute. We're just going to leave those times open. If one presentation finishes fast, we're going to wait till they assign start time for the next one, just so a lot of people are, this is on their schedule. Okay, next slide. Okay, I didn't get into the detailed schedule because it was getting too complicated. But basically presentations are 8:15 to about 2 Pacific time each day. We're 8 or 9 teams. Actually, today we're going to be short. I think we have 6 teams today. There's 24 minutes for the brief. I'm gonna hold you guys to that. I might let you go 25, and then I'll cut to the questions. The questions will go just 4 minutes, and then we have 2 minutes before the next team, and that's mostly so the judges can record their thoughts. And that's a lot of the feedback you get, so it's really important. Okay, Monday and Tuesday we're hosted here at Aerospace. We'll have tours beginning at the end of the day. There's a reception following the tours on Monday. And then on Tuesday after the short Aerospace tour, there's going to be an optional tour at Northrop Grumman. If you're here in El Segundo, you got an email about that, and you should have responded. There's a detailed schedule there. If you use a QR code, or if you it doesn't work on a phone, so but that does give you the time, the name of the track. I don't know why I didn't figure this out. It's like I had the statement of intent. I'm like, that doesn't sound quite right. What can I call it? I'm like, it's a mission statement. Like, I don't know. It took me a year to figure out, but it's a mission statement. So it has the mission statements along with the team name and the schedule. All right, next slide. Okay, disclaimer. I'm not going to read it. Like, you guys can all read. I'll leave it up here for 30 seconds. But if you're in the room, we might take photos of you. And by participating, you're allowing us to use your images, your quotes, whatever. Like we've published a paper about this the last several years. We'll do another one this year. Haven't asked Uche yet if he'll be the lead author, but no time like the present. But yeah, and that's really to help keep the program growing. But we don't claim anything. The ideas you've come up with, those are yours. Next slide. Cosmic background. So, if your students, you don't necessarily know what Cosmic is. You guys all know what ICAM is at this point. Cosmic is a consortium for space mobility and ICAM capabilities. Basically, it's NASA funded, aerospace operated. It's a consortium, brings together academia, government, industry to have a conversation together. So this is a huge part of it. Obviously, all the students are participating, but you also have mentors from government, from industry. The champions are, from government and industry. And really it's a way of connecting. So the researchers doing cutting edge stuff in the lab are seeing the problems that they're having as they try to, raise the Swift Observatory or something. Over 300 member institutions, over 1,200, 1,500 members. I don't know what the latest count is. Workforce development is one of the focus areas. That's what C3 grew out of. And there the idea is not just for college students, but professionals is like, how do we grow the workforce? How do we become more knowledgeable? Okay, next slide. Cosmic Capstone Challenge. You guys should all be familiar with this, but it's we might have friends and family tuning in. So this is what we're here for today. It's a national student competition aimed at developing novel ICM concepts, right? It it is also aimed at growing the workforce, exposing students, but really like the thing we want out of it is like we want that germ of this great idea, and then help grow that. Okay, so we want to leverage our network, connect students to the universities. We want to come up with great ideas and then potentially keep pursuing them. Right, we have some teams from last year that picked up. Well, some teams picked up projects from last year. I had one team from last year working now on a project that's hopefully going to go to the space station. Um, and we talked about like, well, we need a C3 incubator track, right? Which isn't like you're not in C3, but you don't, just because you finish the project, finish the year, doesn't mean that you can't have that mentorship. We're geared primarily towards full year capstone classes because why would you rob banks? Well, that's where the money is. That's where the students are. We love student clubs. We love independent study, directed study. I'm still waiting for my first cross university team. We're open to all of it. But most of the teams are full year capstone classes, and we kind of structure it. We kind of structure the deadlines around that. Next slide. Okay, 4 tracks this year. Orbital manufacturing assembly. That's basically build something in space in a boatswain's locker. Speaking of boatswain's locker, that's Dave Barnhart just walked in the room. He's a leader at Arcasys. They did such a tremendous job this year. They literally designed a box for teams to build their experiments in. Provided the CAD, provided the ICD. Noah's been engaging regularly with many of the teams, along with Dave, and really fantastic. And that's what we wanted to do this year, was have the whole Cosmic membership like be a part of it. Track 2 is lunar operations. Hey, talk about good timing, right? Like go design something to build lunar infrastructure. Guess what? That wasn't a coincidence, right? Because Mark Langley at NASA Langley, like he's been working on this for years. He knew what he wanted to do. He put it out there, and so I'll talk about it briefly. But NASA Ignition, like, hey, tell us what we can do on the moon. Like there's an RFI out there. You guys should all respond to it. Track 30, orbital servicing, Northrop Grumman Space Logistics. They have some amazing missions. Like, how do you build a servicing satellite? This is a little more complex than like track 1, for example. It can be, doesn't have to be. And track 4, in space assembly. How do you architect something when you have these platforms, these designs? Okay, next slide. By the numbers. And I put the precursor stuff in here, just to kind of show how it grew. We went from 3 universities the first year, including University of Texas, El Paso, to 23 universities this year. The teams have grown likewise. We went from a couple dozen students participating to almost 250. We've grown the mentors. We have like publications. I don't even count the publications I do about C3. This is just the student papers or presentations that come out of the work they've done. And I think there were 5 from last year's event. I don't know how many there will be this year. And we're going to cap it at 100 teams. I don't know if we'll get there, but the idea is like, if we have to, I know by hook and by crook, we can get enough mentors for 100 teams. This final showcase would be like really phenomenally complicated to organize, but that's why I'm smart enough to hand those things off to people who are better than I am. Okay, next slide. Oh, yeah, it's last minute prep. You can barely tell the difference. It almost looks like I was in the same seat, but on the left is I was at the Dodger game last year, the night before, or the late afternoon, and this year I was there mid-afternoon. Um, and like every game I've ever gone to with my son, who's, you know, 9 years old and has probably been to like 8 or 9 Dodger games, they've lost every single one. So, anyways, next slide. And then I worked for 3 hours when I got home. Okay, I'm going to pretty quick here because we're running short. We have more than 2 dozen judges. Um, they're like we're going to get 5 judges for every team. Hopefully those will all be live. If not, we'll watch on YouTube Friday, Saturday, Sunday. Fill it out. I normalize everything for the judges for the mix of teams the judges get. It's just plug and chug at this point. Their prize is sponsored by Aerospace Corporation by Launch Systems Division. I'm not going to read those. Track winners were provided the opportunity to brief the champions organization. So the team that wins track one, if you guys want to go out, I'm sure you can go out to Arkansas and present there in person. If that's not practical, you can do it online. Same with, Northrop Grumman's going to invite the team to come out to their headquarters out in Virginia. And the other ones also have virtual invites. Um, the overall winner will be provide the opportunity to brief Cosmic, the community brief. Thank you, Alec, for adding that. And the Cosmic Journal editors are currently working to select the best paper, and we'll invite that winner to publish in an early issue. And we'll also be open to other submissions. And there's a link there. And Rachel, if you could put that in the chat, it's basically like if you have an idea for a Cosmic Journal article, you can submit it. And that could be your project. It could be something else. Next slide. Key dates. If you want to register at university, that's now open. Same with Metro registration. This is really just to get interest at this point. July, like we did a preview release of our info packet last year. We're probably not going to do that this year because it's mostly the same. There's some changes, but I covered them here. We'll probably just put out a webpage with some of the changes. Same plan as next year. Last week, 2 or 3 teams went to NASA Marshall to the lunar regolith terrain and actually tested their lunar prototypes. They loved it. They want to do it again next year. So we're putting that on the calendar. Next slide. Okay, so I highlighted these like track 1 and 3, pretty much the same. Track two, there's some changes. It's specifically to prepare for a fission surface power reactor, just to kind of give it a little more of a discrete task. And track 4, we're looking at in-space construction. One idea is complete the robotic space station. That might change between now and July. Track 5 is brand new. Dispatch space just came out of stealth. And yeah, like they have a reentry vehicle. So I'm excited about that too. Next slide. What's next for you? It's have to go really quick, but if Rachel, you put the links in the chat, submit to SciTech. I highly encourage it, or another conference. Check out the NASA RFI. Join Cosmic, either a university or your future employer. And incubator track I talked about. Ping me if you're interested in keeping to pursue this or keep working on it. We'll connect you with the right mentor. Next slide. Mentor of the Year. Okay. All the teams were provided the opportunity to nominate their mentor as Mentor of the Year. We received many nominations. We formed a committee. It was Christoph, who's in the room here, along with Chris Peterson, and Rana J. Ghosh, who's the chair of the Academic Caucus. They reviewed the nominations, and the winner is Matt Anderson, who is one of my colleagues here at the Aerospace Corporation. He actually mentored also teams from Auburn, but he was nominated by Kennesaw State University. As it was put at the end, if there was more that Mr. Anderson could have done for deep interstellar solutions, we are unaware of it. So he did a great job. He's really dedicated and devoted, and yeah, well earned. I'm really proud of him. And next slide, I think that is it. Tomorrow we'll announce the best prototype winner. And with that, I'm going to turn the podium over to, I believe, the mission for on-orbit servicing and support.
Hello. We are the Mission for On-Orbit Servicing Support, or MOS for short. Next slide. I am Paul Brick. I am the team lead, and today I will be speaking with Chanel Davis, Connor Hall, and Brendan King. We're also joined with Peyton Barnett, Lawrence Valentino, and Parker Scribner. Next slide. We will start by talking about the problem MOS is trying to solve, and then go over our proposed mission. The exact details of our technical details of our mission will be discussed in further detail by my fellow team members. Next slide. So the mission we are trying to solve for MOS is the fact that a lot of space assets have a very large budget, and despite that, they still encounter issues that cause large financial losses. We found from Embry-Riddle et al. On the graph on the right that the two leading causes of satellite failure is the attitude orbit control system and the solar array issues. These systems tend to fail from examples like the Laurel LS-1300, which had consistent solar array deployment issues, leading to a lower than expected maximum power output. Another example is the YAML 402, which had an orbital insertion error, requiring them to use 4 years worth of their propellant to be able to correct and go back to their original orbit. MOS is trying to service both of these issues and similar ones. Next slide. MOS is a satellite designed on the Espostar bus to service these spacecrafts. We are trying to focus on specifically the aging issues of geosatellites, though we can service a wide range of issues. We want to specifically focus on extending the life of these missions. We want to service currently active satellites, as we believe the industry is focusing too much on developing solutions for future satellites. To do that, our system is designed to be scalable for many different sizes of satellites. And so as such, this presentation is built around the NOAA GOES-R satellite as the baseline. Next slide. We are trying to propose two solutions to service these issues. One is the Core Orbital Refueling Kit, or CORK, and the second is the Solar Panel Augmentation Reflector Kit. CORK plans to mount to the engine of the satellite and backflow propellant through the engine to the fuel tank to refuel it. Spark is a deployable reflector shield that can be placed on the client's solar panel and reflect more sunlight onto the panel to produce more power. Next slide. This is an illustration of our proposed mission. We plan to launch, get into geo orbit, maneuver to the client, and perform both servicing operations. If our mission happens or has us servicing multiple satellites, we'll perform a maneuver to get to the second client and perform these servicing operations again. The moment we run out of sparks to deploy or propellant to refuel the client, we will then move safely into a graveyard orbit away from the clients. Next slide. These are two animations of the servicing operation. On the left, we have CORK refueling the apogee kick motor of the GOES-R, and then on the right, we have MOS mounting Spark onto the solar panel and deploying it out. Next slide. Now I will pass it over to Chanel to talk a bit more about CORK.
Lovely. Thank you, Paul. So I'm going to be going over the Core Orbital Refueling Kit, as in CORK. So I'm going to go with the design history, the impact, the requirements, the operations, and the innovation, and then the risk and mitigation. Next slide. So with the design history, there was many different kind of concepts, but we decided to share these three today. So with drill B, it was to reach the client's other spacecraft and then drill directly into it. We didn't love this idea since it will have to get damage to the other spacecraft, and we want to do it in the non-invasive way. The second option was the Northrop Grumman MEV 2.0. So we will attach to they attach to another spacecraft and they'll have a new attitude control system. So yes, it does expand the lifespan of these satellites, but it doesn't solve our issue about refueling in space. And then the last concept we want to share was the RAFTI 2.0 by Orbit Fab. So it's designing a refueling interface to install before satellite launches, so that only solves the future satellites and doesn't address our current issues with satellites in orbit. Next slide. So for the trade studies, we had many different concepts we did, but we kind of focused to show these three today with Cork. So we kind of looked at the damages, the complexity, manufacturability, mounting, adaptability, and repeated use. As you can see, Cork won by an 86%, mainly focusing on manufacturability. It's pretty good to manufacture. The adaptability it can use on many different nozzles is not just for one spacecraft. We're able to adapt it to many different kind of nozzles, engines, and spacecrafts. And then also the adaptability, the damage, and the manufacturability. Next slide. So the impact of current and future missions. So for they were trying to improve current and existing on-orbit spacecraft life. So by refueling bipropellant and monopropellant, and we're not just servicing a single engine or a single spacecraft. We can service many different spacecraft that's current existing. Like I said, we can service to any thruster, any scalable, since our design is we can fit any of those. And then we want a future in space servicing operations. Next slide. So our Cork requirements, we have 8 of them, but our big main ones are 0.1, 2, and like 3. So we want to be able to backflow propellant through an engine and not damage the client's satellite. And we also want to be able to do it autonomously. And then we also want to fit onto SPSR with the mass, power, and volume. Next slide. So here's the operation of Cork of how it works. So as you can see, there's docking and sealing. So we line up to the client's engine, and then once we are docked, we start backflowing the fuel. Next slide. Perfect. So the Cork prototype, so actually we got to design Cork, as you can see in the picture. Thank you, Connor. But we got the engine from our rocket development lab. They let us use a real engine, which is so nice of them. We completed testing, so we're able to seal and track and control the flow rate at varying pressures. Very successful. And then we also have future testing we want to be able to do with different geometries, different size engines, and not just JANISR that RDL did provide for us. Next slide. So our core innovation is backflowing through the chamber, so which is unheard of in space. No one has done it in space yet. So that's why our design is unique and different. And then next slide, we're trying to explain with the catalyst. Next slide. So the catalyst integration is another innovation. So the reaction rate of the hydrogen is deposition is minimized, and when the temperature is minimized, the mass flow rate is maximized. So as you can see in our CFD, with the catalyst and the backflowing, it should work in space. Next slide. So there's we have 4 risks, but the only one I'm going to address today was the catalyst reaction because it caused pressurization. And to minimize this from 4 to 2, we have our CFD simulations and future testing, and to see how that works. To minimize those tasks, there's also 3 other hazards we did address and analyze and find mitigation to use to eliminate the overall risk of our project. But moving on to the next slide. So the next steps is we want to do more research for the catalyst reaction, more CFD analysis, because this is an ongoing with different engines and different nozzles. We also want to do sealing in different nozzle shapes. We only got the JANISR, but we would love to do smaller and bigger thrusters to see if we can scale it and things like that. And then also the microgravity and space fluid mechanics. Since backflowing has not been done in space, we also don't know how exactly what's going to work in that environment. So we want to continue testing and things like that to reach it. So thank you so much. I'm going to pass it over to Connor with Spark in the next slide.
Yeah, thank you, Chanel. So it's a very similar agenda for Cork, so we can go ahead and move to the next slide. All right, so let's take a look at the design history we went through for the Spark concept. So we considered 3 other designs that were not the reflector that we chose. One of those is a spray-on solar panel called a perovskite. This was actually studied on the ISS, and they saw success with actually being able to generate solar power from this spray-on layer. However, it faced degradation issues. Another idea we looked at was to replace the panel completely by removing the old one and kind of soldering on a new one in orbit. And then we also looked at a rollover kind of flexible solar array panel, much like the roses on the ISS, and just kind of roll that over the existing structure and then integrate it into the satellite's electrical system. Next slide. So for the trade study, we looked at 5 major factors. One of those was the design complexity. Another was how much it would alter the MOI of the actual spacecraft that we're servicing. We also looked at the installation complexity, the adaptability, and the ease of future servicing after installation. So the most important of that list would be the installation complexity. So how hard is it to actually mount this device or integrate this device into the client? And then also the adaptability. We want a design that can be useful on multiple different missions. So ultimately the concentrator run or won with a 75%. Next slide, please. So the impact of current and future missions, if you look at the graph in the bottom left, we can see that after about 10 to 15 years, which is a very common or life cycle for a geosat, if not more, you can expect to see about 10% degradation of the solar arrays mounted on the actual satellite. So the goal of the Spark system is to revitalize that 10% and reflect more light onto the panel to get that back up to hopefully close to the operational capabilities that it had after launch. So the Spark device would also be compatible with current and future geosatellites. It would also be easily modified to service different missions. So we could just change out the length, put on maybe a thicker roll, and it could deploy for a bigger array, for example. And then it would also perform or increase performance without need to integrate into the power system whatsoever. So it would be a rather simple concept to mount on and actually get to work. Next slide. All right, so some of the Spark requirements. We had a few main requirements. One is that we need to reflect at least an 11% additional light increase onto the solar panel. We also need to make sure that we don't increase their station keeping. We wanted to target around 5% of the actual nominal capabilities of the client. And then we also need to make sure that we don't break the solar array whenever it's doing maneuvers, and we don't crush the solar cells that are on the actual array that we're mounting to. We also, much like Quark, wanted to integrate requirements to make sure that we could fit the volume, mass, and payload constraints in general for the ESPA-STAR satellite that we are hoping to use on MOS. Next slide. All right, here's a little animation of what the deployment will look like for the Spark concept. This is after it is mounted to the solar panel. The top and bottom of the device, you can see some tape deployable booms. So those would essentially unroll a foil roll and deploy it outwards and basically get the reflector out there onto the panel. Next slide, please. So what is the main innovation that Spark would bring to the industry? So effectively, we want to add a reflector post-launch to extend the life of geosats. A similar concept was implemented on the DART mission, and they had reflectors already built into the solar array. And Spark basically advances this concept, enabling deployment after geo launch on satellites in orbit without integration into actual solar cells or the electrical system of the satellite. Next slide, please. So what are some risks that we found with the Spark system? There were 3 main ones. We want to make sure that we don't crush the solar cells or the solar array. We wanted to look into the uneven deployment of the top and bottom booms, as that could be an issue, and then also tearing the super thin reflector film. So we mitigated those risks by propagating the motor or clamping device down into the arm that would be mounting it, allowing more control and kind of a bigger system to control those forces. For the uneven deployment, we wanted to implement we did implement a common drive shaft between the 2 booms, so they will always deploy at the same rate. And then for the reflector film, we are going to implement kind of a carbon fiber or fiberglass weave on the back. So if a rip does start, it would be terminated at the intersection of the weave and the foil. Next slide, please. So what are the next considerations for the Spark design? Well, we want to look more into the incident angle efficiency losses. So we want to propagate the client for each mission around the Earth and around the sun and kind of find the average incident angle that would be hitting the solar array and then design optimally for that incident angle. So kind of change our reflector mount angle to make sure that we're getting the best reflection onto the actual panel. We also want to look more into our reflector material. Currently, we have aluminized mylar as our choice, but I believe that we can find a better reflector that would reflect the 400 to 1600 nanometer wavelength band that gallium arsenide panels like to absorb. And then third is the heat degradation from increased sunlight. So we want to look into exactly if we do put more solar flux onto a gallium arsenide panel in space, how does that exactly affect the lifespan of that panel, and what does the degradation rate look like if we were to reflect more sunlight onto it? And now next up is Brendan King with integration and feasibility. All right.
Thank you, Connor Hall. And I'll be going on to a little bit more about how all this integrates within the overall MOS system. Next slide, please. So starting off with our mass propellant budgets, looking at the individual systems of Quark and Spark, down the bottom right corner, we can see that Quark and Spark both come in combined under 180 kilograms. If we take this into account with our ESPA-STAR dry mass of 450 kilograms and a propellant capacity of hydrazine at 710 kilograms, which accounts for external fuel tanks attached to the ESPA-STAR payload, we come in at a total of 1340 kilograms. Looking at launch providers, we found that Falcon Heavy provides a direct to geo mass of 6,000 kilograms, which means that we could potentially launch up to 4 MOS missions to geo on a single Falcon Heavy launch. And we can also do rideshare missions as well if we have a single MOS payload and be able to cut our launch costs as well there too. I'm looking at our propellant budget. Once we get to direct to geo from, say, Falcon Heavy, it'll take very minimal delta V or propellant mass to moving between clients if we want to service multiple different clients, as well as our graveyard orbit insertion. So this leaves around 690 kilograms of propellant left for refueling, which we can add to potential satellites. And an example of this case would be if we look at GOES-P, for example, it can provide up to 1128 kilograms, which means we can almost fill that entire thing up by half of its propellant if we were doing a single mission. Next slide, please. I'm looking more into our power and volume budgets. Here on the right of the screen is a scaled image of the ESPA-STAR payload areas, as well as a Quark and Spark model to scale. So overall, Quark and Spark models come in at a much smaller volume than the overall payload, which means that we can be very modular and maintainable and add in these multiple Quarks or multiple Sparks to fit within a single ESPA-STAR based on the mission profile or what we are trying to service. I'm looking into power consumptions. We're available from ESPA-STAR. We have 1,200 watts of power. With both Quark and Spark combined under less than 800 watts, this gives us enough margin to add in different sensors or other things that we might need for, say, for example, our pod operations or other needs as needed. Next slide, please. Looking into our data flow, we're going to have to communicate with our client satellite to perform our mission. So overall from our client, what we're going to need is to talk with the client valves, make sure that all the valves are in the correct configuration, be able to perform that backflow operation. In terms of power generation as well as fuel tank capacity, we also need those to make sure that the operations are performing as intended for both Quark and Spark. And then we're going to be connecting with the ground station for those communications, as well as MOS will have its own internal data flow within the ESPA-STAR bus to perform these operations as intended. Next slide, please. Looking into manufacturability, we definitely thought about manufacturability from the start. So looking at our CAD models, we've done both detailed CAD models for Quark as well as Spark, and have had full-on bill-on materials where all of these parts are pretty easily accessible, can be purchased online or COTS off the shelf. And we view that these can be done, manufactured and tested in less than 5 years or less, which means that we can rapidly bring this online if we were to, say, have a mission that would be needing rapid iteration or rapid need for our Quark and Spark solutions. Next slide, please. Looking into our technology gap, the biggest thing is going to be, we've done our experimental data from our CFD simulation, which we built off ANSYS Fluent, and the results seem promising, but we would definitely like to make sure and get some experimental results as well to make sure that the backflowing process is indeed what we expect. And so that's why that one's at TRL level 3. In terms of our Spark design, we have 2 main ones, our specific composite layup design for the tape truss. We need to have that specific design layup to be able to do that rollout operation as intended. And then as well as the clamp mechanism, we have to make sure that prototype is tested and built to ensure that we have minimal damage or proper connection with our client satellites that we are servicing. Next slide, please. In terms of our mission costs, We went through and used the NASA Advanced Mission Cost Model, which is a parametric cost equation and cost estimating relationship. And so going through and following the calculations as shown on the right, we come out at a total cost of $81 million for one ESPA-STAR module with our Quark and Spark solution. Factoring in our launch costs, we come out at $245 million. And so that includes our Falcon Heavy launch as well as our ESPA-STAR module. Next slide, please. And so how this compares to say a GOES-P satellite or GOES-R satellite, we come in at a savings of around $128 million. And so this is great because it shows not only our solution can save money, but it also allows that satellite to stay up in space longer, reducing the need for, say, sending up an entirely new satellite to replace that satellite. We can just directly go in there and service them and keep them up there longer, which definitely reduces the cost. And so we deem that our Quark and Spark solution has potential to save the industry money as well. Next slide, please. Looking at our major milestones, the MOS team was formed and our project manager was selected in late August, and we started completely from scratch this semester. And from there, we've just basically been full steam ahead, working on major milestones with the Quark milestones shown in blue here, such as SRD or system requirements documents, CDR, PDR, and tackling all those milestones throughout the entire last 2 semesters, as well as our Spark milestones shown in yellow, which we started mostly in January, and those are continuing through. And once we go back, we'll continue doing testing on Quark and Spark. Next slide, please. Looking at our final summary. In summary, MOS servicing will include our Quark and Spark operations, which will tackle our rank 5 and rank 10 tasks of on-orbit refueling kit and solar panel augmentation. For Quark, we'll be backflowing propellant through the satellite thruster to refuel hydrogen fuel. We'll be able to service any GEO satellite that has a hydrogen thruster. And again, the servicing design has never been done before, so that's where our innovation really kicks in. In terms of Spark, we'll be adding a reflector to increase our solar flux on degrading satellites. We'll service any GEO satellite that has a solar array. And a similar design has been proposed, but never been fully designed and implemented. Again, showing that innovation. Next slide, please. In terms of our future work in our path to PDR, we plan to finalize client platform, specialized design inputs. For Quark, we want to complete our catalyst analysis and potentially get experimental results to support our findings. We want to perform space environment dynamic simulations to make sure that we are able to conform to our space operations in that space environment, which is very dangerous. In terms of Spark, we want to develop and test our deployment mechanisms and go through these other things that we have listed here as well, and deliver a full scope preliminary design review. And I'd like to leave you with kind of viewing, you can view Quark and Spark as kind of tools. If ESPA-STAR is our toolbox, we're just adding tools to that toolbox and potentially leading the way into adding more and more tools down the line. Next slide, please. In terms of paper, if you want to learn more about our project, feel free to, we have submitted the paper to the C3 final showcase, and we do plan to participate in AIAA SciTech for 2027. Next slide, please. I'd like to end with some acknowledgements. Thank you to our faculty mentor, Dr. Fan, who's in attendance today, as well as Dr. Haslam, for our C3 mentor, Rob Briz from the Skyway organization, from our school, Embry-Riddle Aeronautical University, and our College of Engineering, Cosmic C3 organizers, and everybody else who has helped us greatly in our design. We are deeply grateful. Next slide, please. Here's some of our references. Next slide, please. And with that, thank you very much for your time, and we're free to take any questions.
Okay, do we have any questions? Andy, can you step up to the microphone?
There you go. Sorry, I'm late. A 3.5-hour drive to get here. And I may have missed it, but give me a little more information on your Quark design, as in how much did you leverage off really the only 2 that are out there right now, the Northrop's passive refueling module and Rafty's OrbitFab's Rafty. How much of that influence your design for Quark?
We definitely took a bit more influence from the Northrop design, just due to them trying to mount through the engine. but we specifically wanted to pick a simpler option. And we thought that the Northwood option, which more or less added a completely new add to control system, was way too complicated. And instead we tried to rely more on what was already on the satellite. And so we try to make it simpler than that by just refilling their propellant tanks and just having them basically operate normally, but with just more propellant. And with Orbit Fab, because their kind of refueling panel required implementation on future satellites, we thought that kind of the timeline for that design to be implemented is too far in the future, and it'll be a lot easier to specifically create a design like Cork that can right out the box be used on current nozzles, as long as you have the geometry to kind of design Cork around.
Guys, good work. What did you learn? So you did hardware testing.
Yes.
So what did you learn so that you didn't get fed?
Oh, well, yes. Yeah.
Well, so far we're still in the middle of testing. We have performed the first start of our leak checks. And so far our system is working, but we have yet to do an actual full scale like flow through. And we at least plan to try to prove that our system, specifically our prototype, is trying to prove against the nozzle sealing, as that is what we believe to be the hardest mechanical challenge. And we want to kind of expand our testing in the future with more complex systems, incorporating a lot more of their fluid system and a lot more realistic of a thruster. But right now we're just doing fluid tests, making sure that that sealing location on the nozzle does not leak.
Greg, I see you have a question online.
Yeah, I wanted to know, you've talked about checking the leak through the thruster. What kind of analysis did you do on the spacecraft bus design itself, the valves that they have through their prop system to show that they could accept backflow?
Yeah, so a lot of the problems that we deal with is people don't like publishing their fluid systems, which is pretty understandable, to be honest. One of the things that we have to do is we have to make some assumptions on how it works. So we pulled off experience from the Rocket Development Lab and pressure-fed systems, which are analogous to what you'll see in a spacecraft from what we could find. We looked at specific valves and locations for things, and we identified that for the most part, it's very similar to a liquid rocket we'd build on campus. So things like check valves, specific locations for those where they're located is stuff we looked at. One of the big things we noticed is solenoid valves are present on spacecraft a lot, and they don't like flowing backwards. So it's a management problem to make sure that you can handle that when you put a negative differential across it and you end up opening the valve like a relief valve, essentially. That would be most of our analysis. Again, like if we could get more information on fluid systems for those spacecraft, it would be excellent. And in a real mission scenario, of course, the client would be providing that information.
Okay, and we are at time. So I want to thank again the team Moss from Embry-Riddle, and we can take 2 minutes for the next team to get ready and for the judges to record the scores. Thank you. Like, is anyone else a judge here today that wants to actually?
Better do it online. You do it online. Yeah. It's your intro.
Or sometimes days, more or less.
Yeah. Yeah, let's do it.
Okay, next up are the miners.
Hello, everybody. We are the miners. We are from the University of Texas at El Paso, and this is our Cosmic Capstone Challenge for track 1. Next slide, please. So first, we are going to introduce ourselves. So my name is Rowan Espinosa. We are all undergraduates in mechanical engineering. We also have Juan Luna, who unfortunately could not be here today. And we have John Smith, and we also have Vanessa Preciado. We all worked on pretty much CADing, researching, and on this presentation and on the report. And also on the bottom of the slide, you can see our past team members as well. Next slide, please. And here are our advisors. So we had Dr. Angel Flores Abad, who is an associate professor at UTEP and Aerospace and Mechanical Engineering. And we also had Alexander Pustinger, who is a PhD student and our mentor, who is also in mechanical engineering. Next slide, please. So first, we're going to start off with our mission objective. So pretty much it was to adapt the boson locker into a multifunctional manufacturing station. We designed a locker that integrates 3D printing, soldering, and also wire embedding. And pretty much the system can manufacture 3D printed objects with embedded electronics, which can have multiple use in spacecrafts. As you can see in the picture on the right, we'll be focusing on 3 main parts, which is the gantry system, the tool exchanger, and also the multi-axis print bed. Pretty much the system was designed for using commercially available parts for maintainability and also ease of assembly. Next slide, please. This is our problem and also our value proposition. So this design can extend the operational lifespan in many ways, including solder joints, and also it can adapt to many different types of tools because of our rotary tool exchanger. And we have our target market there at the bottom of the slide, which would be satellite manufacturers and operators. We also have commercial space organizations and government space agencies as well. Next slide, please. So we have our innovation. We used space-grade polymers like PEEK and also Ultem 9085, and to ensure a high thermal stability and structural reliability in vacuum environments. It currently adheres to NASA standards for additive manufacturing, and it can adapt to many different tools into the system. And also, while most systems only 3D print, this boson locker can also add soldering and also wire embedding in one sequence. Next slide, please. And this is a general review of our system. So we'll be going on to the next few components, which would be the gantry system, the multi-axis print bed, and also the tool exchanger as well. Next slide, please.
Where's the control for this? All right, so excuse me. So big inspiration for this is obviously additive manufacturing. Some of the processes that we chose of the 3D print, wire embedding with the 3D print and soldering, even though they are very similar processes, they do require different tool heads in order to make that happen. So we looked very hard into how are we going to change those tool heads. Of course, we wanted to come up with a very rigid design that to eliminate any kind of slop. So right here, we just kind of got a concept of how that would function, how that would work. Obviously, locking keys that would made up with our alignment slots to pick up the tool off of our rotary exchanger. Then that rotary exchanger would swing the unused tool out of the way for our desired printing operations. Next slide, please. There's just kind of an image of our gantry system, once again inspired by 3D printers out there that are out there. This is the backbone of our operations. We plan to have it run off of timing belts. And this portion of it is what is going to give us our translation in the X and Z axes. Next slide, please. Now our multi-axis print bed. This is this particular component of the entire design. We expect will be able to give us our other 3 axes of movement. So we're going to end up with a total of 5 degrees of freedom. The hot plate will be able to rotate 360 degrees. It also has a tilt mechanism, which we know from our CAD will give us at least 20 degrees of tilt, both positive and negative. So we think we can get some pretty interesting design geometries out of that. It also translates back and forth into our y-axis. Next slide, please. The rotary tool exchanger, obviously the other important component here. Not only does it store our tools to keep them from floating around inside of the bosun locker, but it shifts them in and out. We wanted to make sure that this was designed pretty robust, and it's integrated. All right, next slide, please. All right, so our risk, we use kind of the standard model, likelihood versus consequences, to identify our risk with this entire system. They kind of really focus into 3 main categories. One is, thermal, thermal temperatures and keeping that under control. Of course, the laser and keeping that into safe operating conditions, and then FOD. We're looking at working with soldering. We're looking at using filaments for our 3D materials, and of course, the embedded wiring, making sure that's clipped and cut so we're not having, any foreign objects floating around inside of the locker. We believe we can mitigate most of that through our testing on ground, in the vacuum, and with our next steps. All right, next slide, please. Once again, just kind of an overview of our risk analysis here. Really, much of this is kind of what I said. And then kind of a nice little image there of a concept of what one of our tool heads would look like as well. So this one in particular, that is, would be the laser and the soldering kind of device. This is loosely modeled off of a device that we have working in our mentor's lab. So we do know and do expect that it will function within our expected parameters. I think we're back to you. Next slide, please. Oh, excuse me. We do have an animation right here of the locker. And what you're just going to see is this thing kind of spin around. You're going to next notice our print bed rotating. Bring our tool head down to conduct its soldering operations. And then I tried to capture here an image of, the trading of the tools. All right. So with that, now it's back.
Okay, next slide, please. Guess we're going through the animation one more time. All right, so this is the storyboard for our concept. So while we're down here on Earth, we'll fully assemble and secure the bosun locker prior to launch with all the integrated subsystems. And then we'll launch it up in a spacecraft, and it can be used while in a spacecraft to produce any manufacturing operations. So that could be damage to a satellite, can be damage to a spacecraft. And then we can also adapt it so we can host it on any hubs in space, like that could be the ISS or any other hubs. And then it can either stay in those hubs or stay in the spacecraft and then come back down to Earth as well. Next slide, please. So this would be our results for this project. So we have the thermal simulation, the power consumption, and also our FEA analysis. Next slide, please. So here we have our heated printing nozzle. We did a thermal simulation on this tool head, and we wanted to see if we can print with the nozzle and see how the nozzle will react to those certain conditions. So here on the picture on the left, you can see we did a low emissivity simulation, and the picture on the right, you can see we did a high emissivity simulation. So in the low emissivity simulation, we had high temperatures of around 1000 degrees Celsius and also a high heat creep. And then in the high emissivity simulation, we had a max temperature of around 460 degrees Celsius and also a lower heat creep as well. And the environment was assumed to be negative 270 degrees Celsius and convectionless as well. Next slide, please. So this would be our power analysis. So we broke down our components and we calculated the max power and also the general operating power. So one of our requirements was to ensure the system was within its limits of 1000 watts peak and 300 watts continuous. And so we calculated that the total maximum power was around 430 watts. And also our general system power was around 150 watts. And so you can see that we were definitely under those limits. Next slide, please. And then here we have our structural analysis. So we did this FEA simulation, or sorry, this stress simulation on the gantry system. So we put the loads down towards the top of the gantry system, as you can see from both of these pictures. And we actually had a safety factor of around 15 throughout almost all of the gantry system, and only had a maximum displacement of 0.05 millimeters, 0.45 millimeters, as you can see on the left picture here. And so we can see that the gantry system is reliable under these conditions. Next slide, please. Pass it on to Vanessa.
Okay, so for our future work, we plan to validate and refine a system as we move toward a working prototype. The focus is on making the design performs reliably under real operating conditions. This includes the building prototype to verify the tool changing. Sorry, I'm short, guys. Testing performance under high temperatures and improving alignment for consistent accuracy and ensuring debris is properly contained. Next slide, please. So we met most of the we met all the requirements for the Archises bosun's locker and that are fit for the, sorry, let me say it again. That it's fit for the Archises bosun's locker and with the integrated mounting interfaces. Our total mass is 8.78 kilograms and our power consumption peaks 430 watts, giving us significant safety margin under the 1000 watt locker limit. The all structural components use space grade materials and ensuring compatibility with vacuum and thermal conditions. And finally, our system operates semi-autonomously using simple command inputs, meeting control and operational requirements. Next slide, please. For our trade study, we guided our decisions based off performance, reliability, and simplicity. For the structure, we decided to go with aluminum for strength and thermal performance. For thermal management, we decided to go for a passive cooling. For thermal management, cooling to reduce complexity and power usage. For motion control, we ended up going Sorry. Give me 1 second, guys. I'm sorry. Okay, sorry. For our motion control, we use stepper motors to achieve precision without adding unnecessary cost or weight. And we develop a simplified linear tool changing system to reduce mechanical risk. We ended up going with additive manufacturing, FDM, to minimize material waste and allow the complex internal geometries needed for integrated wire embedding. Next slide, please. For our control architecture, we enabled the system to operate reliably and autonomously. At a high level, we used dual controllers set up to handle motion control and processing efficiency. And our system integrates real-time sensor feedback to maintain precision and prevent errors during operation. It operates semi-autonomously, executing complex tasks using simple command inputs and designed it with separate power systems for stability and standard communication interface and monitoring and data transfer. And to conclude our last slide, we successfully developed a multifunctional semi-autonomous manufacturing payload. For our key achievements, we integrated 3D printing, soldering, and wire embedding. We achieved a 15% mass reduction and maintained a 57% power safety margin. We validated structural and thermal integrity through rigorous NASA standard simulations. Next slide.
All right, thank you guys. Now you guys can ask some questions.
Okay, let's open up the floor to questions.
Hey, you guys, I think on your risk slide, you said something about like wire stripping and having a problem with that. Do you guys know what type of wire stripping tool head you would use? Would you do like mechanical or like a thermal insulation removal?
John.
So really, we didn't mean stripping wires themselves. We just mean that the wiring could strip off of, the motor. So we could end up with some, oh, excuse me, I'm taller. So in the design that we probably should have worded that a little better. We weren't talking about stripping the wires because we envisioned for the wire embedding that it would be coming off of a spool of just naked wire.
Gotcha. So it's more like damage as you
more damage
deposit
of
that
the wire as we're maybe cutting, maybe we a piece fragments off or something along those lines. So more along fragmentation would probably be a better word.
Cool. Got it. Very cool. Thank you.
Awesome. Thank you. Yes, sir.
So UTEP has the Keck Center, which is I've worked with for about 15 years, world class in additive manufacturing, particularly electronic printing. Did you utilize that information at all? That's right in your backyard. And second question, you mentioned briefly about changing direction or something happening at the beginning of the semester. You didn't drop everything you learned and start over, did you, at the beginning of this semester?
Changing direction. I'm not.
I heard you say something about the beginning of the semester you started over. I think those were I wrote down the word. Like something had changed. Did you change the design midway?
No, we did not change the design. However, the team very much rolled over.
Okay, maybe that was it.
Yeah. So the team that like this challenge is a capstone challenge. So across 2 semesters. So unfortunately, our team members from the previous semester, they all graduated.
But of course, they documented everything
They
so
did.
well.
They documented everything so well. And they handed it on over. They did a fantastic job. And we were able to take what they had and run with it. So I'm not sure if maybe that was what got kind of.
I might have picked it. Okay, translation. So can you mention anything about the Keck Center and how it influenced what you did?
I cannot. Can you?
Yeah. So the Keck Center obviously did provide us with a lot of resources, especially with the research that they've done. And also our mentor here, Alex Bissinger. He's also works there in the Keck Center, and so yeah, he did he provided a lot of his research as well to help us with this project.
Hi, Alex. If you are there, feel free to expand and elaborate more, please. Alex Pustinger, are you there?
Hello?
Yep.
Here we go. So yes, the research over at the Keck Center does do the electronics fabrication using like industrial printers that have been modified up to the wazoo with undergrad, how would I say, mechanical force to strip a lot of the industrial parts. So, but the research is kind of like the bare bones to embed wires, laser solder, and provide electrical components to it. So that's a lot of my research that was inspired into this. We use similar processes for here. It's a little bit more nuanced in this case. It's into a smaller configuration, as mine almost takes up whole room. So does that answer your question? Okay, cool.
So one question I didn't see, the assumption is you're going to create something inside the locker and then get it out. Was there did I miss it? Are you assuming that we open it up, or is it just manufacturing and then the locker is taken off and taken somewhere else? So what are that kind of?
Yeah, so
Part in and out.
yeah, we can get the part in and out of the locker. Yeah, just to manufacture the part inside of the locker. But yes, it can be taken like in any spacecraft, and well, it can be adapted into any spacecraft.
And I think part of it is that they're explicitly like these are intended as demonstration missions, right? Like to show you can integrate it through the technology. Then the next step is, yeah, like it plugs into the ecosystem, right? And so I have two questions. Like are there any other questions? Because I have two. Oh, okay.
Hi, I'm curious about the power consumption by purely the 3D printers, 3D printer alone. Does that account for the thermal environment in space, or is there more to be determined? Because as far as I'm aware, something like a 300-watt printer is more suitable for on Earth.
Yeah, so it does account for the conditions that are in space as well, the power consumption.
And just to follow up on that, like you did the thermal analysis, which was good, and it showed, okay, we want something high emissivity, so we get more heat away, but you were still over 400 degrees, right? And the question is like, is that survivable, right? Like that's something to consider. And then the other part is like the bosun's locker, like they have some thermal control capability, right? So have you considered like, okay, do we need to plug in so they can take some heat away? Or is this a low enough temperature that we're good as is?
So the thermal simulation was to see if the heated nozzle can still print while under those conditions, and obviously like in those extreme conditions, it does heat up really quickly. But while I do think it still is survivable under those conditions.
It would require thermal testing in the vacuum.
Yes.
And then the next question is, obviously you designed this for being in orbit in a bosun's locker. Like what would be different if you're doing this, say, on the lunar surface? Does that make it harder or easier, or pretty much the same challenge?
We had not considered those two different environments.
Yeah.
Okay, we have a couple extra minutes. If anyone has a question, they can come off mute, or anyone else in the room. And I think Alec or Rachel, if you can confirm, I think the next talk has been withdrawn. So after this, we'll go into an extended break. Is that right?
That is correct.
And then we'll be back at 10.
I believe, just one moment, we will be back at 10 a.m. Pacific time, 1 p.m. Eastern time.
Okay. So thank you all for getting us off to a great start this morning. Thank the UTEP team again.
Thank you, everybody.
And now judges are gonna score and we'll go into break and we'll be back at 10 a.m. Pacific, 1 p.m. Eastern time. Thanks all.
Thank you.
Yeah, we're gonna get started in 2 minutes here. The next team up is Flexion. So if you guys are here, you should come to the front. And we'll get started right at 10. So just 1 minute.
Hello, my name is William Dortch. Jonathan Sanchez.
I'm the team lead, Matthew Loy.
I am Kin Sang.
And we are Team Flexion. Next slide. Next slide. So to start our presentation, we would like to just briefly go over like a brief summary of what we're going to be talking about. For one thing, we'd like to talk about some problems that we want to address, mainly being that right now, the Artemis missions on the lunar surface is mainly based on trying to extract resources and use them and convert them into reusable like energy sources or turn them into air or fuel. What we're trying to target is the short operational and mission time of exploration rovers on the lunar surface. And we want to address the fact that these exploration rovers were going to have to enter these extremely deep craters where there's no visible light at the bottom. And we're also going to be addressing the fact that currently solar panels degrade pretty quickly on the lunar surface due to dust accumulation. So our solution is to essentially autonomously assemble a structure to generate the power and store the energy for long-term use that will then be utilized by a wireless charger to charge rovers. Next slide. So to go over some benefits of our system, utilizing NASA's Viper rovers as a baseline, they are currently self-reliant on a solar panel system. So during the lunar cycle, when we eventually lose sunlight, the rovers are essentially entering hibernation state until next period of sunlight where they can operate. So our proposed method of generating this power and storing it for later use allows us to increase operational uptime, that being approximately 18 hours every single Earth day, which is a 50% increase over the Viper rovers' current uptime of 12 hours. Next slide. Next, we'd like to address some locations and some environmental issues. So for our project, we wanted to target the Shackleton crater. Due to the depth of this crater, there's essentially no light, known as a PSR or permanently shaded region. For our project, we're going to be placing our project at location A, which is approximately at 89.68 degrees south, 166 degrees west, with this location being a peak of eternal light, meaning that it experiences more sunlight than every other place, with the longest period of darkness only being about 7 days. Next slide. Next, I'd like to go over the requirements of our project. These were these requirements were developed based on the Viper class rovers in terms of the total amount of energy we need to store and how much power we need to generate. And along with that, we have also considered the environmental constraints, such as lunar dust accumulation. Next slide.
All right, so for our building block for this is going to be the Armadas voxel. It has pretty much a cubic tehedral complexion. It is by 1 foot by 1 foot by 1 foot, so overall volume is going to be 1 feet cubed. To assemble these structures is going to be the sole E, which the whole purpose is to transfer these building blocks transfer the building blocks for the robot for the MMIC to go ahead and connect and mate these once we provided the code and the structure design for it to get programmed and assemble these in together. Next slide. So here's our CAD design. It is composed of 20 feet. It is 20 feet worth of voxels with 4 legs. And then the top structure is going to be the solar panel. It has 48 panels with 32 Armadas voxels that are going to be supporting the solar panels. And the power length from the structure down into the crater is going to be 3.2 kilometers with the guy wire to go ahead and help support it in case of vibrations and any buckling that's going to occur. Next slide. And here's the guy wire and how it looks. Pretty much just helping creating tension to the ground to avoid it from being toppled over and any stresses that occur from the weight from the top. Next slide.
So now I'd like to go over some trade studies on how we developed our project. For one, we'd like to go over the different battery storage technologies to be able to store all that energy for the rovers to use. We compared different materials, but the most important one was lithium ion, as that's currently being used. We compared it against solid state batteries, lithium sulfur, and sodium ions. And we found that the solid state battery was the most optimal solution, as due to its higher energy density, we could have lighter batteries. We could transport lighter batteries into space, along with its higher life cycle, meaning that we can effectively recharge and discharge the battery twice as many times as, say, lithium ion. Next slide. So next, I'd like to go over the power generation and panel orientation. So essentially, we looked into different ways to generate that power. Our first option was looking at just essentially reflecting the sunlight into the crater, where we would place solar panels to generate the power. We also looked at adding a heliostat to basically track the sunlight. We also looked into NASA's current mission of trying to develop nuclear fission reactors. And lastly, our chosen method, which we are going to use, which is generating the power at the ridge of the crater, and then using a transmission line to deliver that power down into the crater, into our batteries and charging station. As for the solar panel orientation, we looked into different form factors, one being a pyramid, a cylinder, and a block, which is what we're calling it. So each design would have its own unique panel tilt, the pyramid being 45 degrees, a block and cylinder each having 88.5 degrees to have perfect angle of inflection with the sunlight coming in. But the main thing that caught our eye for the block was mainly due to the fact that it required the least amount of voxels. So it wasn't that complex to assemble. Next slide. So after all these trade studies, I also performed an analysis on the power and energy performance. So essentially, we are going to be generating anywhere between around 500 watts to about 650 watts throughout the cycle. And we compared it to the overall load, where as during the period of sunlight, we are going to be utilizing the battery and the solar panels to both charge the rovers during this time period. And when we enter the darkness period, we're only going to be utilizing the battery to charge the rovers. Next slide.
So kind of taking a step back a little bit, we actually want to go over the assembly sequence as to how we want to be able to establish this charging station on Luna. And so essentially it will start off with our payload, and our payload will be broken up into 3 different packages. There will be the electrical package, the mechanical package, and as well as that, the robotic package, which is basically the robotic package is having our SOLI and our MMIC. Next slide, please. So kind of going over the electrical phase and electrical assembly, we first want to establish the main components that's centered around the electrical assembly, which is being able to have our solar panels, as well as having our solar panels, having our solid state battery, our guide wire, and as well as our charging interface, which is we're using an inductive resonance charging interface. And from there, kind of analyzing how we would go about being able to assemble this is already having pre-built modules. And essentially what we would do is we'd have our DC solar panels connected to our solid state battery, which would be our main DC source. And then from there, we would have our power inverter, which will kind of, basically mask AC waveform. And then from there, it will go into our transmission coil. And from going into our transmission coil, then it will go into the secondary side of our coil. And that will mainly be how we established before our rover that we're essentially modeling. Next slide, please. So kind of what's really important about being able to design your charging interface and having an inductive resonance charging, coil is essentially the coil geometry, and as well as that your materials and how you want to use your coils. And so it's important to, basically emphasize having a good quality factor. And this basically determines the range as to, an intermediate range or a short range as to how you want your electromagnetic wave to propagate in space in order for it to effectively create a effective charging or magnetic coupling. And as well as that, understanding that based off of our quality factor, you want to be able to minimize losses, but as well as that high switching, so that way you can have a high level of reactance. So you can go to the next slide, please. And what it should look like is our curves here. When you have an efficient, charging interface, essentially your coupling would, kind of ramp up exponentially. But specifically, what I want to point out is, kind of the bottom right graph, you can see that, you have your power reactance that's going up, and as well as that, you also have your power delivered that's going down, and as well as that, you have a small amount of gain. That's actually a bad graph, and that's on purpose. And the reason why it's on purpose is because, something that's really key is being able to, if you were to actually design this correctly, and be able to align your coils in the proper, coupling, then your losses, so you're reducing your resistance. So your losses would essentially kind of, be flatline. And as well as that, your gain will kind of shoot up exponentially. And as well as your gain shooting up exponentially, you will also have high reactance. And that's extremely key to being able to design the wireless power transfer, our inductive resonance charging circuit. Next slide, please.
And as for the structured, and in order to see if it even withholds all the weight on top of it, I went ahead and created a simulation here. We're curious on the material strength. So given that it has the whole solar panel structure above, which equates to about 11.72 newtons worth of force downward with the moon's gravity of 1.62 meters per second squared, it accounts for all the screws, the solar panels, the voxel weight. Went ahead and applied this to the legs. And here we're given the report of the SolidWorks simulation here of a about 10.1 megapascals. I think it's, yeah, 10.1 megapascals. And then the overall conservative strength of the armor dust voxel was 31.1 megapascals. So it's about 1/3 of its strength that's being applied, which is pretty safe to say it's not going to have a material failure. So we're going to move on into the buckling stage and see if it's going to have any problems there. Next slide. So with the so analyzing with the buckling strength here, given that the outputs of 1.34 of a buckling factor, it is a little bit concerning that it's getting close to the failure, say to 11.72 versus the 115.72 of a critical load. So it is concerning that it may experience a failure over time if as it accumulates weight and with dust or anything of that sort. So another solution that we have was the guy wire, which also helps relieves the stress from the building itself. All right, next slide. Oh, and for the active thermal management of the battery and the components, we're pretty much using the electric resistance heater, mainly because it has a pretty simple unit. There's a lot of less for a mechanical failure to occur, and that can be said with the heat pipes, exchangers, and the liquid circulator. Compared to everything else, was a lot more complex, and the biggest factor that it draws power. If we're trying to conserve power to power these, you don't want a lot to go to waste, and just keeping the battery and the components in a stable temperature range. Next slide.
So now that we've defined the parameters and also the model of what we're trying to build, we are going to have to actually build it. And as mentioned before, we're going to use robotic agents to do it. But more importantly, what I want to discuss here is automation. Why are we automating this? Because number one, of course, this is track 4 and C3 requirements, everyone, more importantly, though, the point of C3 track 4 is that we want to automate lunar manufacturing to do 2 things. Number one, it's that lunar manufacturing can be done autonomously, and we don't want to involve human agents to do it. Number two, those human agents can now go ahead and do other things they're on the moon to do, which is to do scientific research. Also, what is worth mentioning is that there is no definite proof that automation works, because it is ultimately a system that has to be regulated by humans over time for conditions. So how I'm going to demonstrate that this is possible to automate this project is that I'm going to provide you with some of the components of automation, and I'm going to describe the steps that we are going to take to automate this, and then that's how we're going to prove that this project can be automated. So here we can see that some of the things that I consider to be important to automation includes data, feedback, and also asynchronous instruction. More specifically, how we're going to automate, or what operations we're going to do to automate this. Separately, if we consider this from a control systems point of view, what we're trying to get, or what we're going to put in is some design. The thing we're going to try to get out of it is the structure it builds itself. In the middle, we put a feedback loop for if the robot screws up, then we correct it. Next slide. So first things first, the data we're going to put into it is the project design. We're going to break down the project design into special code, as in figure 1. We break that down into numbers that machine can understand well. And so we take each position of the voxel, and then we assign it, we assign like the center coordinate of it to a point. Then we can convert all this into something that machines can understand, and then we copy that to the robots themselves. The robots are loaded with a routing algorithm, which is to say, it will find the best routes going from a point to another point. One of the algorithms that NASA proposed to using is the ACER algorithm, which without going into detail, and also providing a snippet of code in the figure 2 gives you a sense of sort of what the data in the automation we're using. This will help speed up the build if we use routing algorithm. Otherwise, we're going to resort to defining each step of the movement as some sort of slow one step here, one step there, and then it becomes unoptimized. Next slide. Next, we build our feedback loop. So each of the robotic agents have on board a ESP32 chip. More importantly, it has wireless communication among each other so that they can provide stuff like temperature, belt, like terrible belt movement, with figure something out in case the robots fail. Maybe retry a step or something. Next slide. So finally, we put our components together. We have to have 3 steps, or 3 threads or operations. First of all, we're gonna have to break down our simple human readable design from just a CAD file into something that a robot can do. So this is we're gonna consider this the pre-operation. We parse the design and then we break down and then we move to the next step, which is operation 1. We plan an efficient algorithm for routing so that the robots can move efficiently. And then as this operation happens, we load in another operation, which is the telemetry operation, operation 2. It monitors the physical status of each robot, and then it sends the states back to operation 1 to account for some sort of error in the routing, which is to say, if the robots fail, then they have to repeat a step. And then the robots have to recalculate what steps they want to take to be efficient again. So we go back to operation 1, and all of this until the design is completely built. Next slide. So a curious discussion came up during the planning for all of this is that when I considered automation of this, I find that like partially if we're going to do it all on board the device or on the robots, we may run into the issue where the processing power due to the battery size is limited. We may not actually be able to make the robots route themselves efficiently. So then I came up with the idea that why not use a server to do it, some intermediary, which this turns the robots into something that's not fully autonomous, which could be an issue. But to break down why we're still on track, if we're saying that we're going to build this manually all by hand, saying that like the command center sends commands directly to the robots to move themselves, then that will break number 1 the challenge, and number 2 that will require extra human hands to do it. So if we consider a half state, a semi-autonomous method to do this, where we're instead of having the agents on board do the calculations, we use a server to do it, then we find that now if we have more designs that we want to do, then those robots can be packed up and then put back onto the new voxels. And then for some other designs, those robots can be reused. Next slide.
Next, I'd like to talk about scaling. So obviously our project was designed to service 1 exploration rover. So in order to scale this up for say 2, 3, however many rovers you wanted to do, we wanted to go over some rules on how to do so. For 1, if you say you only want to do 2, you would just simply double your energy storage requirements and your power generation. But say if you wanted to do 3 and over, you would need to do the same thing, increase your energy and power generation sources. However, you'd also need to increase the amount of charging stations that you'd have. We'd recommend that each charging station supports up to 2 rovers. So say if you had 6 rovers you wanted to service, we'd recommend 3 charging stations. This is due to the fact that these rovers are charging for 3 hours and that they can only operate for 9 hours. We'd also like to mention that when increasing the solar panel height, that the tower's maximum height should only be capped to 60 feet and no larger. Otherwise, it would become unstable. And for redundancy's sake, and to ensure that you always have power in case of any failures, we always suggest that you try to evenly split your power generation across several towers as much as you can. Next slide. So to go over the summary, essentially, we talked about how we're essentially going to be creating a solar tower that will generate the energy for a battery for exploration rovers to use on their missions. And some potential challenges that we have are mainly due to automation, being that the current robotic assemblers are not going to be able to connect our transmission cable to our wireless charger, and nor are they going to be able to bolt the guide wire into the ground, and those would require additional new robotic assemblers or would require astronauts to do so themselves. Next slide. All right, thank you. Any questions?
Okay, let's open up. Do we have any questions? Go ahead, Andy. Make sure the mic is on.
Yeah, low, yeah. Really liked your approach. Didn't like the answer, but I liked your approach to the automation. I personally believe as soon as you get man in the loop at all, you get a problem because he's going to make something go wrong. And so I might have come to a different conclusion that you needed semi-autonomous, but it was a very nice logical step through of the trade. And that was very, very impressive the way you thought that through. Question about, and related to that is, there's a lot of things we can do on terrestrial or in space with robots. The advantage of on terrestrial, and by the way, I favor space, but on terrestrial, I can check it out. I can test it. I can run it through things. I can look at it in a SEM or in put it on a vibration table. I can't do any of that in space. So I would have liked to have seen some addressing of what the challenge is by making your assembly on the lunar surface and all the issues that will occur, even with a semi-autonomous, with having to deal with making sure it's good. Because, on Earth, you'll make it, you'll test it, it's going to look great. You'll even put it in some environmental facilities. On the moon, you'll make it, but, are those weld joints right? Are the attachments aligned properly? There's so many unknowns, and you don't have the facility or the personnel on the moon to go up and look at it and measure it and do all sorts of things. Or if you do, it's very expensive to do. So would have liked to have seen some addressing of that. And if you can, talk about that, that'd be great. Thanks.
Yes, thank you for the question. This is a contingency that NASA has been well aware of, and that's why they built so much coding into sort of like at the minimum, like here's like the easiest way you can see that they did this is that there are data packets that they send back to from not just each robot, but the components of each robot. So for example, the Sol E is controlled by two microcontrollers. Each of them controls 3 different motors and also 2 grip motors. They have to send back data such as belt slips for the motors. So if in case that on the moon that like the motor slipped, that means that the movement becomes out of sync with each other. So and also with the MMIC-I robot, which is the worm-like robot that goes in between the voxels, they they tell the robots what the post width modulation commands, whether commands were successful or not, and also if there were any sort of power bridge issues type of thing. So this is one of the things where I've thought that like having an intermediary like a server would be clever with, is that like instead of now having the question of, oh, did the robot reboot itself, then that all that data gets processed in a server, and then so you can tell, so like the intermediary server can sort of do like, maybe you put A on it and do some sort of intermediary like diagnosis. Oh, it finished rebooting, but it's still doing the same thing. Then what happens? Ultimately, when it comes to a robot being dead on arrival, that's something that a human has to actually like go and interact with. It can't just simply replace itself.
Okay, we have time for one more very quick question. Oh yeah, Greenfield, go ahead.
Hey guys, this is Greenfield from NASA Ames. Good job going through the mission design scenario and working through the issues of these how these types of systems would work. My original question was related to how you guys would do the guy wire, but it seems like you guys left it as an open challenge that needs to be addressed. But the other question was how would you guys do a surface interface? How does it interface with the surface at the base, and how do you guys deal with that problem?
So the original plan was to essentially well, I guess it wouldn't exist yet, but essentially take like a very long kind of like a long screw, maybe like 3 or 4 feet, and it would get dug into the ground. And from the other end of the guy wire, we would essentially like, I wouldn't say tie, but like hook onto one end of that wire to basically hold it down.
I see there's another question, but Harsh, if you put that in the chat, because we are at time. So let's thank Flexion once again. The next team is the Space Pirates, and they are presenting remotely. Well, why don't you guys just wait 1 minute so the judges have a chance to finish recording their scores.
Yeah, sounds good. Are we coming through all right?
Loud and clear.
Perfect.
Okay, just another half minute here. Some of the judges are still recording their scores.
Yeah, all good. Did you want us to go ahead and share our screen to present the slides, or were you going to do that?
Yeah, we will present them.
Okay.
So.
Okay, sounds good.
All right. Yeah, I think you guys can get started.
Okay, awesome. Well, hello everyone. My name is Dominic, and we are the Space Pirates. So I'll start off just by introducing the team. If you could go next slide, please. So I am the project manager, and I'll just have everyone introduce themselves as they come up to present their own slides, but just here is our breakdown in case you wanted to look at it. Next slide, please. Okay, so we're going to talk about the mission overview now, and next slide. Yes, so some background and motivation. That graph on the right, that shows the annual number of objects launched into space over time As you can see, in the last couple of years, it has grown exponentially as we become more reliant on satellites and technology. So in order to combat this, we developed the spacecraft platform for autonomous repair, refuel, and orbital work, or Sparrow, which should hopefully increase the lifetime of satellites that are already in orbit and reduce the need for us to keep launching more. And you can see our target orbit is listed at the bottom of the slide there. And next slide, please. So what will Sparrow do? It will perform critical servicing functions on the client satellites. So that will be things like upgrades, repairs, refuels, pretty much anything that will help extend the lifetime of our client satellites. And how it will perform those servicing functions. It is a modular spacecraft, so our payloads are hot swappable and customizable depending on what the clients need. And our main payload that will be performing those functions is the robotic arm. Next slide, please. Okay, so to figure out our system requirements and our success criteria, we looked at the stakeholders and their needs. We've outlined some of our stakeholders here, the most important ones being DoD and regulatory licensing guidelines with things like debris mitigation and launch safety protocols. We also need to be able to fit inside the payload bus of our launch provider, as well as dock and grapple with the client satellites, and that will be done via the robotic arms. Next slide, please. So here is our success criteria. If all of these things can be completed, then the mission will be considered a success. For autonomy, we need at least 90% anomaly resolution success, which is just off nominal conditions that the onboard computer and AI should be able to handle. We also need to be capable of servicing at least 2 clients per mission. Even if the mission doesn't call for it, we must have that capability. For our critical servicing functions, we need to be able to perform at least 2 of the ones that we have outlined. We must also be able to provide at least 200 meters per second of delta V for client repositioning, at least 90% debris removal success rate, either from the client, around the client, or on the way to the client. And we also must demonstrate augmentation and have a 200 liters of usable stowage for replacement parts, which is shown with our modularity. And next slide, please. So here are some of our system requirements. There are a lot more, but we outlined a few on this slide. These ones mainly discuss the modularity and reconfigurability of the spacecraft, as well as the autonomy, which is very important. And next slide, please. So now we'll go over the system concept and architecture. We will start off with the system architecture. So this block diagram, on the right, you can see the system as a whole is the spacecraft management system, which we have broken up into the launch vehicle, the spacecraft, and the ground team. The scope of our project was the spacecraft itself, so we've broken that up further into the servicing/payloads, ADCS/GNC, spacecraft life systems, which is our power, propulsion, and thermal structures, as well as our communications. And you can see these line up fairly well with our sub-teams listed in the second slide. Next slide, please. So now this graphic represents our concept of operations. If you look in the top left corner of the graphic, that is where it starts. The spacecraft will be launched from Earth, placed into its parking orbit. From there, it will use modular payloads and the robotic arm in order to service our client satellites. If you look at that bottom right corner, the third part, the satellite must be capable of transferring between our parking orbit and the client orbit in order to rendezvous with the satellites. Our spacecraft must also be capable of being serviced while it's in orbit, whether that's from other Sparrows, other satellites, or docking onto a station somewhere. It needs to have that capability of being serviced. And it will just continue this cycle of completing missions and being serviced until it eventually gets decommissioned. And next slide, please. And this diagram shows basically what a mission will look like for Sparrow from the point of view of the spacecraft. So once it is placed in the parking orbit, it will wait there until it receives a client request. From there, calculate the optimal rendezvous maneuver to the client, avoiding debris if necessary. Then rendezvous with the client, perform the servicing function. If there are more clients to be serviced in the mission, it will repeat that loop until it gets to the final client. From there, it will return to the parking orbit and wait for further instructions. And next slide, please. Now we have David to go over the overview.
Howdy, I'm David. I will be going over the Sparrow and its general structure and design. Could I go to the next slide, please? So this is Sparrow. This is our hexagonal prism shaped spacecraft. We have a 4 solar panel array system and 2 robotic arms on a track that will have access to all faces of the Sparrow, and will be able to access all the modules, which you see in the dark gray on the top section. On the right, you can sort of see a skeletal view of this structure, and we have segmented it onto the next slide, which demonstrates 3 primary segments. If you could go to the next slide, please. So the primary segments are the propulsion structure, the avionics and computer structure, and the servicing module structure. The propulsion structure contains 4 tanks, 2 propellant and 2 oxidizers. The avionics system will also have stowage space as well as the avionics and computer systems. And then the top section will contain 2 tracks with robotic arms on them, which will operate on rails to service all sides of the satellite, and also contains the modular compartments themselves, of which the what is contained in the structure will be determined by the client. Next slide, please. So this is the propulsion structure. It is it's designed to maintain rigidity during launch conditions, and also keep the propulsion tanks extremely rigid. And we use the primary plate to be CNC on 2 sides so that we can have a very modally capable structure. Yes. Next slide, please. So this is the modular payload structure. We went with a sort of design that has all faces being the servicing functions themselves. And so each panel can be removed, and each servicing module can be removed, replaced, and hot swapped or upgraded, and will be interchangeable depending on the client's mission. This module also contains the almost all the cameras for the satellite on the top, and as well as, of course, the rails. And then next slide, please. And following a similar concept for the electronics bay, each panel is removable so that all the electronics can be accessed, as well as everything that is stowed there, like bits and other electronics and replaceable parts. And that is the structure. And so on to our next section.
Howdy, I'm Nate. I'm part of the GNC team. I'll be talking about some of our rendezvous and proximity operations simulation that we put together. Next slide, please. So we used a software called Basilisk to put this sim together, and we modeled a 6 degree of freedom rigid body dynamics. And we have our ADCS in the sim, and all we did was we put our actual sensor noise into our ADCS from our data sheets. That way we can analyze the capability of our ADCS during the sim. And some of the requirements we had was that our attitude error was within 3 sigma, and our angular rate error was within 3 sigma of those data sheet specifications. You can move on to the next slide, please.
So I'm Juan. I'm going to be talking about the determination of optimal maneuvers for orbit transfers. So to determine the optimal transfer for our satellite, the Rishi client satellite, we used the Lambert solver, where we looked at the departure time of our satellite from its stationary orbit or parking orbit, and we also looked at a range of time of flight. And in each of these values, we calculated the delta V. And after we solved for all the ranges, we looked at the minimum delta V, and that would correspond to our optimal transfer maneuvers. Next slide, please.
So these are some plots we obtained from the simulation to validate our ADCS. The one on the left is our attitude error out of the filter, out of the UKF during rendezvous. And the one on the right is the IMU angular errors during rendezvous. And you can see that for most of the sim that they are well within those 3 sigma bounds. And those spikes are due to guidance mode changes. So we have several guidance modes. We have sun pointing, ground pointing, velocity pointing, and target pointing at the spacecraft. And next slide, please, is where we have our video. So, and you can put that in 2 times speed for, sorry. Okay. So here we have a detumble phase where we're stabilizing our spacecraft and charging our solar panels to sun point.
This stage for pointing our satellite towards the sun.
Yes, that yellow vector there is the point to the sun. And then here we are establishing our comms to a ground location. And you can see in the beginning, we did a little stabilization again. So we're pointing our comms devices at the ground, relaying telemetry data, all that good stuff. And then we're receiving a servicing request here to go ahead and service the target satellite, which we then will switch to rendezvous phase where we perform a Hohmann transfer. The first burn is a plane change and a altitude change. And then here we are rendezvousing. So here, this is where we'd also change our guidance mode into from sun point to hill point. And then once we reach a relative distance to the target, then we'll change our attitude again to lock on the target with our camera and sensors to inspect and make sure as we're approaching everything is as it should be in case we need to do any hazard detection or maneuvers. And then here we just modeled our relative motion using the Wiltshire equations for simplified relative motion. Sorry, I guess it cut out there, but
and this scenario, the solar panels will be tucked in. The thing is, we used a Vizard with Basilisk, and unfortunately we couldn't tuck in the solar panels to demonstrate in this stage.
So then here we'd adjust again so that we make sure that our arms are pointed to the servicing target, and we would have our sensor here performing, looking at the spacecraft, making sure everything's okay, and also diagnosing and determining which servicing function we need to perform. And that will conclude the sim on our part.
So my name is Jacob Bustamante. I'm with the structures team, and I'll be presenting the start of the sizing and trait studies. So next slide. Next slide. Okay, so the structure requirements. So here on the left are the structure requirements. Structure shall withstand first mode frequencies greater than 150 and 50 hertz in both the longitudinal and lateral axis respectively. The structure shall comply with size constraints of the launch vehicle payload. The structure shall have a mass less than the maximum allowable payload of the launch vehicle. So this preliminary sizing here on the right is based on a max payload of 150, but these were subject to change, and they actually did change as we were designing our system. So next slide. So materials trait study, as you can see on the right, this is our criteria, and titanium and stainless steel stood out, but we decided not to go with titanium, instead go with aluminum due to the machinability and cost. Next slide. And our shape study, our criteria is on the right here, and we went with the hexagonal shaped satellite due to its modularity and ease of integration. Now with propulsion, power, and thermal.
Next slide, please. Well, hello, my name is Ali Garcia, and I'm part of the propulsion, power, and thermal sub-team. And I'll be going over the trait studies for this section. Next slide, please. So here are subsystem requirements. These were our main motivators when it came to this trait study, and with helping to choose components. I won't read every single one of them, but as you can see, those are our requirements. Next slide, please. Here we have our assumptions taken and our sizing for the subsystem. For example, our payload 150 kilograms at 10% dry mass. Our propulsion system 2.5% dry mass. Power at 10% dry mass, and thermal 5% dry mass. These were kind of the main assumptions taken throughout the trade studies, as well these equations. For example, the rocker equation helping us find the delta V for our propulsion side, and then our solar panel, where our equation where we compare the power with the sun angle, helping with the power system. Next slide, please. Here for a delta V requirement, our system goals was to autonomous service at least two clients per mission, as well as at least 200 meters per second delta V capability. We did a couple Monte Carlo simulations, which helped us determine our 4,000 meter per second delta V capability explained in our subsystem requirements. Next slide, please. For propulsion, we considered 4 different propulsion systems: chemical, electrical, nuclear, and solar cell. Some of the criteria looked into for this was its maneuvering capability, thrust, system mass and volume, power requirements, and complexity. And as you can see through the averages, our winner was propulsion, mainly due to its maneuverability, reliability, high thrust, and it had the lowest mission time. Next slide, please. For power, so no power equals no mission. Here we considered 3 different power systems: fuel cells, RTGs, which are radioisotope thermoelectric generators, and then solar cells plus batteries. And some of the criteria that we that helped us determine this was its continuous power criteria, eclipse performance, specific power, complexity, and modularity was a huge driver in this trade study. And our winner was our solar cells and batteries, mainly due to its reliability and its high modularity. Next slide, please. For thermal, we considered 2 different thermal systems, active and passive. Some of its criteria were control authority, adaptability, power usage, complexity, modularity. And as you can see through the table, it was way too close to call, so we decided to go on kind of a mix of both. For active, we stuck with more electro heaters, and with passive was multi-layer insulation and radiators. Next slide, please. And then here are some thermal simulations. These simulate the servicing mission and return to parking orbit. Our internal temperature must be around 0 to 20 Celsius. And as you can see on the top right graph, our peak temperature was around 15 degrees Celsius. And that's well within our target range for a thermal system. And that concludes the propulsion, power, and thermal subsystem. And on to our next slide, please. On to our computer systems.
Howdy, I'm Calvin Schrader. I'll be going over the computer systems. Next slide, please. So we have a few subsystem requirements. Basically, for communications, we need to be able to connect regularly and often to the ground station to receive information about our client satellites. And then for command and data handling, we need the ability to run our AI models so we can perform without human in the loop intervention. Next slide, please. For the command and data handling trade study, our main focus was on the location and the type of AI. Due to latency, power demands, and then also the development timeline, we decided to go with specialized onboard AI models. Next slide, please. For communication, we looked at trade studies for space-to-space and ground-to-space communication. We looked at RF versus optical. Due to the infrastructure and lack of signal loss, we'll be going with RF communications for both space-to-space and space-to-ground communication. Next slide, please. For sizing, we looked at the power of our payload to get the power of the total system, and then we did basic parametric sizing to get initial mass and power budgets for the computer systems. Next slide, please.
Howdy, my name is Carson. I'll be going over the attitude and GNC systems.
And just a time check, you have 3 minutes.
Okay, so thank you. Just like some of the subsystem requirements that you saw in the sim. So the ADCS system shall determine the spacecraft's relative navigation, as well as the attitude rates, and should be able to control the spacecraft accurately as well. Go ahead. Next slide, please. This is just a little bit of a closer look to the ADCS system that was active during the simulation you saw earlier. So on the left side, you can see the suite of sensors that Sparrow is equipped with, which the sensors are fed into the navigation, UKF, which is fed into the guidance. Algorithms fed into the control. For control, we've got reaction wheels, magnetic torquers for desaturation of the reaction wheels, and RCS thrusters for more fine maneuvering. Next slide, please. We've got just a little layout of the location of all the sensors, where they would be on the Sparrow. The star trackers, sun sensors, magnetometers, RCS thrusters for 6-degree freedom control. Of course, internally, you've got the magnetic torquers for desaturation, IMUs, reaction wheels, just all the sensors that were active during the simulation everywhere. Next slide, please. Yes, and Paso.
Howdy, my name is Sean. I'm going to go over risk analysis and PDR plan. If you can go to the next slide, please. So this is our risk analysis. It's a very standard risk matrix, ranked 1 through 5 in severity and likelihood. We identified several key risks that could happen at any point in the mission. Those are A through H, and 3 of those were in the red category, which means it's a mission failure. We absolutely cannot proceed with the mission if these persist. So we need to do some mitigation. If we can go to the next slide, please. So here are the mitigation strategies for those, including using more thrusters, training AI models, redundant sensors, and using modular interfaces to mitigate all those. We go to that next slide, please. And here's our post-mitigation risk analysis. All of those have moved down to the yellow category, which means mission is a success. We can build and launch Sparrow. If we can go to that next slide, please. And our PDR plan is very standard here. It's going to be a 6-week plan from today. We have 5 distinct phases that focus on selecting specific components and making sure we meet all subsystem requirements, system requirements, and stakeholder needs. Next slide, please. And now for some lessons learned. Next slide. Some innovative concepts that we explored. The first one were robotic arms on circumferential tracks around the spacecraft, which we already outlined. These allow for a full 360-degree authority around the spacecraft. They'll be highly effective in accessing multiple servicing locations. Next is something that we really wanted to do, but it was beyond our scope and very complex, that being an orbital docking station, which is more so like a garage or a gas station in orbit. Sparrow can go rendezvous with it, get new parts that clients send, and refuel. And thirdly is the fully modular payload compartments, which were the ultimate driver in the design of Sparrow, which we also talked about earlier. Next slide, please. And now for a technology gap. These things all exist today currently, but they do need significant R&D before we can build a launch Sparrow. That being the AI, autonomous robotic arm, and a high-powered onboard computer that is effective with all the data processing in space. Next slide, please. And now we have some of the biggest challenges that we came across, that being the size constraints, making sure everything fits inside of our payload. We did have to increase our payload, or our launch fairing, from the Falcon 9 to the Starship, and also how we were going to do the high modularity, which we talked about. And finally, our system level integration. So all systems engineering aspects of it, making sure subsystems interface, and also keeping a master equipment list and a bill of materials. And that's going to be it. Thank you so much for listening to our presentation. If you have any questions, please feel free to ask.
Okay, go ahead, Andy. Try to keep the answers crisp.
Yeah, this was really well done, very well organized, a lot of good content. In fact, I had to really search to find something wrong, and a couple things jump out at me. Is you're concerned about size, overall size, and the reality is what you needed to do is say that with this baseline structure, I can service 80% of the satellites that need help, and if I went up 10% in my size, now I can do 99% of my candidate satellites. So I would have liked to seen some assessment done of what the customer need, the client needs are, particularly in regard to size. And the other one is you talked a little bit up front about your refueling capability, but I know you're not going with the capture aspects of it, but I sure would have liked to have seen a hydrazine or electric propulsion tank or something on board your configuration that shows you even can do that. So it wasn't either left out or for some reason not part of it. But thanks.
Yeah. So thank you, first of all, for saying all that nice stuff. In regards to the propulsion, we had planned on one of those modular modules to be dedicated to propulsion. So it would store things like a hydrazine tank or an oxidizer tank. And then using the robotic arm, it would be able to take that tank out of one of those modules in order to install it onto the client satellite. But yes, you are correct. We did not include any image or anything like that in the slides.
Do we have any other questions from the judges? Anybody else?
I have a question as to why you guys chose to do a like in orbit and then you get called to the servicing mission versus doing a kind of on demand, like you get the request to service and you build the satellite and then launch it up per mission basis versus like a, you know, in orbit constant station.
Yeah, I think the main reason that we wanted to choose something in orbit is just due to the launch cost. If we went the way that you're suggesting, we would likely have to spend a lot more to launch a Sparrow every time that we get a request versus if we have one or multiple already in a constellation, then once we receive the request, they'll be able to be dispatched to the client satellite. And it also is much quicker if there is, say, a critical emergency with one of the client satellites. Our satellites would be able to get there within a couple hours versus a couple weeks if we were to build it on the surface and then launch it up there.
All right. Thank you again. Let's thank the Space Pirates, and we're going to take just 2 minutes while the judges record their scores.
Thank you so much.
Okay, next up, the last briefing before we have lunch here on the West Coast is the Astrobotics from Purdue University. You guys are welcome to proceed.
All right, cool. Can you guys hear us perfectly fine?
Yep.
All right. Well, thank you guys. So just to start off, as mentioned, we are Astrobotics from Purdue University, and our project is focusing on the VLA robotic arm framework. I just want to give thanks to our advisor, Elizabeth Kung, and mentor, Harsha Malshe. Next slide. So what do we accomplish? What's the goal that we're trying to achieve here? So our problem that we decided to tackle is that current ISAM robotic systems require a lot of human in the loop involvement, which introduces not only latencies, but it also drives up mission costs as well as limits on orbit operations, especially if you're trying to scale or add new operations, new tasks, so on and so forth. And so what we propose is a platform agnostic, fully autonomous software framework that can use as foundational vision models such as LAVA VLAs, and it enables all types of robotic arms, robotic manipulators to execute any series of tasks, whatever that might be in the space environment. And this can all be done through high-level natural language supervision from an operator. And how we solve this problem is it eliminates the need for algorithm pre-programmed scripts, and it allows natural language to be issued by the operator, either that is on the aircraft, or it could be on the ground, and they can send it via uplink or downlink. The system also fuses vision plus force sensing to make sure that the tasks are autonomously executed robustly. And for this scenario, we chose 3 different operations: pick and place, riveting, and screwing. And this allows us to demonstrate the complete assembly capability for our operations. And our status is that we were able to finish the conceptual design, did our trade studies on the various frameworks, which we'll discuss later in the presentation, and showed a proof of concept via a simulation, which will all be discussed in this presentation. And on the right, you can see our robotic arm that we took and modified and made respective tooling for our specific scenario. Next slide. So just to introduce the team, my name is Ankur Sanapati. I'm an ECE major here at Purdue University, and I'm the project manager of this group.
Hi, my name is Ritik Jayaraman. I am a sophomore here at Purdue, majoring in computer science.
Hello, my name is Elaine Lee. I am a junior in aerospace engineering here at Purdue.
Hi, my name is OJ, and I'm a sophomore studying CS here at Purdue.
I am Ekansh, and I'm studying computer science here at Purdue University.
Next slide. And here are program management milestones throughout the course of the year. In September, October, we decided what we really wanted to do, what we wanted to tackle. We then created our SRR, made our overall requirements that we decided that we wanted to tackle, did our midpoint showcase, completed all our trade studies, and then finally, near the end of the stretch in March and April, we finished our technical paper and completed all our simulations and established that, yes, VLA can be possible in our specific scenario that we're talking about. Next slide.
So what exactly is the problem and why does autonomous assembly matter? First of all, orbital operations are incredibly expensive and inefficient. So for replacing a single satellite in geostationary orbit, it would cost upward of $350 million. As for cost on human factors, every 1 hour that astronauts spend in EVA, they must undergo 10 hours of training, which is a lot on time spent in order to train these astronauts to perform these operations. As for core problems with our current ISAM system, the core challenges involve continuous human-in-the-loop approach. That means that every command needs to travel from ground and orbit to back, and latency is introduced, which limits precision in assembly making and real-time operations. Furthermore, dependencies on these issues will limit factors such as mission cadence and the scalability of our current orbital manufacturing infrastructure. Therefore, what we are proposing is a solution based on a software-agnostic approach, which will serve as a layer between our high-level command from an operator and then the operation actually performed by the robot, which will enable independent and also autonomous operations performed by the robotic system itself.
Next slide.
As for our storyboard for concept of operations, we first have our launch, which means that in this case, the payload will be stored inside the bosun's locker and secured in a folded configuration. It is folded since due to launch vibrations, which will ensure that the robot arm will be able to survive these conditions. Afterward, it will deploy. The robotic arm will deploy once the module actually reaches our target LEO orbit, and our bosun's locker will activate. And then after that, the system will initialize. So we'll check camera settings. We'll verify that the software actually works within the system. And then we'll test actually commanding it. So the operator will issue a high-level natural language command in which the robot arm will determine the best steps in order to perform that operation.
Next slide.
Our next 4 tasks include the operations actually performed by the robot arm. So we have 3 main operations, which we'll get to in a bit, which is pick and place, riveting, and also screwing. As you can see on the right, we have an example of the environment, which is great, that can be screwed and riveted in order to perform these operations. And then after the robot arm performs this, it will be able to verify and report that the system has succeeded or failed, and then the operator can confirm commands for our next task.
Next slide.
So here are the 3 operations that we chose for our system. The first in pick and place. Using this operation, the arm will be able to use camera vision in order to identify a target component. It can then use this tool in order to grab the object and transport it to where it needs to be in order to perform operations. The next is riveting. This is our permanent connection that we chose for our robot. In this case, we're using a low-power self-piercing rivet in order to improve structural integrity. This is what we chose since it does not require pre-drilling of holes in different components. And our last operation is screwing, which is the automatic screw driving using a rotary and end effector attachment. This is used as our non-permanent attachment. So this will enable components to be screwed and also unscrewed for further operations.
Next slide.
At the core of our autonomy layer is a vision language action, or VLA model. This utilizes the transformer architecture, which is the same technology behind these popular AI chatbots such as GPT. However, instead of generating text, our VLA generates physical movement. Because it's trained on massive datasets, it possesses generalized physical reasoning. This makes our hardware completely hardware agnostic. We can swap out the robot arm without having to perform retraining en masse. The VLA possesses a spoken command and live video to generate a task plan in just 2 to 4 seconds. Once the VLA decides what to do, our deterministic vision pipeline handles the how. To maximize reliability in space, we purposely color-coded our critical tools. This lets our vision system instantly segment the camera frame, isolating the target with sub-pixel accuracy. We then deproject these pixels into 3D world coordinates with under 0.1 centimeters of error. These coordinates feed directly into our classical robotics layer. Our inverse kinematic solver then calculates the required joint angles, guaranteeing 4 millimeter positioning accuracy at the tool tip. Next, our motion planner generates a completely collision-free trajectory throughout joint space in just under 5 seconds. Finally, the arm executes the movement, and then from start to end, from the initial operator command to the completion of the physical task, entire pipeline completes in around 30 seconds. We'll go more in depth about the specific type of VLA that we chose in later slides.
Next slide.
In addition to our software pipeline, we also evaluated the feasibility of our mission. Our current proposal, it complies with the Bosun's locker, not only in terms of space, but also in terms of payload. Mass, we currently estimate around 80 kilograms as an upper bound for our mass constraints, and for power as well. We currently estimate our peak draw power to be at around 270 watts. Additionally, we aim to use technologies which had a moderate to high TRL level. For example, for VLMs, VLAs have been used in robotics, terrestrial robotics before, and they are currently at TRL levels 4 and 5. Additionally, other operations such as thread screwings are at TRL level 7. However, the challenge is going to be in the integration and adapting these ML inference pipelines to space-related compute, such as using hardened variants of like the NVIDIA Jetson Nano, and validating that this pipeline works in microgravity.
Next slide.
In addition, we've created a 5-year pipeline to be designed and built and launched. Our first 18 months will mainly be more of our PDR, where we focus on ground testbed validation and model optimization for edge compute. Then we'll focus on vacuum testing and vibration qualification in years 2 to 3. And then in years 3 through 5, we'll focus on integration with the Bosun's locker and the port architecture, while finalizing on the unit build and then launching at the end of year 5. We've also listed our bill of materials here. Note how these bill of materials have no component which is specific to our application or robot itself. Again, this is because of the hardware agnostic quality of our solution. You can see an example of our picture of our simulation here on the right side, where you have the green end effector tooling, which is our grabber, being used to pick and place a grate or a panel onto a yellow base. We have a more in-depth video and explanation of the simulation later in our presentation as well.
Next slide.
Additionally, we have estimated uplink and downlink constraints for us. Uplink should be pretty simple because the operator will just need to act in a supervisory capacity. All they should need to uplink is the natural language commands that the user wants to have completed. So for example, pick up the orange grate. That would be the command that would be sent to our system. In terms of downlink, it'd be a little bit more comprehensive, where we need to send compressed camera images just for verification that, hey, our system is actually working. We'd also be sending down telemetry logs and post-task assembly inspection images. So overall, around 5 to 10 megabytes we estimate per assembly cycle. Again, the operator is supposed to be in a supervisor role only, which is why our uplink and downlink constraints are pretty lax.
Next slide.
For easy of measurement of our required elements, we split into 6 main categories, with green meaning that we have completed that requirement and orange meaning that we are still working towards that. The first requirement is whether it fits within a assigned volume. So our 6-DOF arm will need to fit within the Bosun's locker. And since we are using a software agnostic solution, which can be applied to different robot arms and not a specified one, we are using a resized model of 1/2 scale for our UR5 arm, which has a total movement range, including all its operations in the arm itself, of 15 by 15 by 16.75 inches, which fits within the given dimensions of the boson locker. Next is whether the arm or our payload is within the mass and power. So our estimated payload mass is about 80 kilograms with the 400 kilogram limit. We estimated 80 kilograms, which includes the robot arm, all the toolings, the toolbox, the environment in itself, and also the electronics needed in order for the arm to fully operate. And then also we have an estimated peak draw power of 250 watts with a sustained 180 watts, which is within the 300 watt limit as well. Next requirement is whether the bus supports operations. So the boson's locker provides power, data, and structural interface, which means that the robot will be compatible with architecture. Next, our launch and descent environment. As stated before, during launch, we have our arms stowed in a folded configuration. This is to better it to survive vibration analysis, but also we need to get data on that in order to further test that as well. Next is demonstrating useful capacity. We have our 3 operations: pick and place, riveting, and screwing, and we have deemed that necessary to complete a full structural assembly workflow. And the last one is appropriate analysis. We still need to work on thermal analysis and information on that, on heat distribution, dissipation, and also structural FEA in order to make sure that our arm is able to sustain all loads during operations.
Next slide.
Now, if we look at the broader technical impact, this mission represents a shift towards persistent orbital operations. By removing the need for constant human-in-the-loop control, we enable a level of autonomous assembly that simply has been possible with traditional teleoperation. What's particularly valuable here is that our framework is platform agnostic. Because the intelligence is software defined, it can be deployed on existing robotic arms. This means we can give current servicing vehicles advanced assembly capabilities through a software upgrade rather than a hardware redesign, which has the potential to save millions in development and launch costs for legacy systems.
Next slide, please.
Now, our core innovation lies in the first ever application of foundation vision models, specifically the VLA and Lava class architectures, to ICM assembly. Current on-orbit systems are almost entirely dependent on pre-scripted motion or direct teleoperation. We've moved beyond that by allowing the robot to reason about its environment in real time. We've also decoupled the intelligence layer from the hardware, so the same model can be reused across different missions and arm configurations with minimal retraining. Furthermore, our natural language interface allows a mission controller to direct complex sequences in plain English rather than programming joint trajectories, significantly lowering the barrier for operators.
Next slide.
Now, this capability is designed to advance Cosmic's highest priority missions. By mastering the chain of picking, placing, and fastening, we provide essential toolkits for missions like the autonomous payload swaps on platforms like the Arctic Port. Our framework also scales to assembly of large modular structures and the on-orbit replacement of outdated instruments on client satellites. Essentially, we are providing a bridge for the ICM ecosystem to move from one-off technology demonstrations to a future of routine modular spacecraft assembly and servicing.
Next slide. Now, for this one, we have a simulated video. If we can click on it and we can kind of talk about what's going on here. So this video, just to note, is 4x speed. So right now, the operator, let's say, issued a command saying, please go and grab the orange grate. So the robot processes this natural language, finds the correct tool to use from our toolbox, which is red, green, and blue, finds the right orange grate that we're referring to and goes to it, and then picks it up and places it over the yellow panel. Then after that, the operator will issue another command, which is now screw the orange grate to the yellow panel with the blue, pink and brown screws, which is kind of hard to see in the video, but we labeled them pink and brown. And the robot, once again, understands the natural language, figures out what types of tools it needs to use, and then goes forth and does the command autonomously and robustly, all within like 0.4 millimeter accuracy. So this video kind of shows how if an operator was to issue any sort of natural language command, then the robot will not only process it and reason through which tool it needs to use to proceed with the task, but it will also go forth to executing these autonomous operations itself. Because not only do we use a VLA, but we tie it in with IK or inverse kinematics to ensure that the robot is autonomous, and robust in every single task that it does do. And once again, this is trainable across any task, so we just have to fine tune the VLA such that for whatever task the operator requires, it is capable of doing that. Next slide, please. And so we did go forth and do a trade study on the various decisions that we needed to make throughout the project, one of which being a fission model. And right here, what you see are the results of our trade study. So we had option A, which is obviously our VLA models that we've been talking and discussing about throughout the presentation. But we also looked at something called Dino, which is essentially a software which doesn't use any natural language component to it. Instead, what it does is it takes in the image of the environment and then segments it so that it essentially creates vectors and bounding boxes for every single object that might be interactable. Now, the only thing with this is this removes the natural language component that we wanted to strive for in our system. And it just does not, it's not quite software agnostic. And so for that reason, we decided to continue with VLA and Lava. And as we saw in the simulation video, it is completely feasible. Now, VLA does require quite high hardware, like it requires around 10x compute costs compared to Dino, for instance. But Lava is a much smaller version. It's much quantized, and it removes most of the backbone architecture that we don't need in VLAs, like in traditional VLA methods, which is why we went forth with the VLA method and more specifically with the Lava method, because it's optimizable and much more easier to run on space-grade hardware.
Next, we also did a comparison on the proper types of joining methods, both for reversible and not reversible. For the not reversible, we are looking into welding and also self-piercing rivets, and we ultimately chose self-piercing rivets due to the low power and no need for pre-drilling. As for welding, since it has a risk of debris and also heat generation, we decided that going with self-piercing riveting would be a better choice for permanent joining. Next, we also went into reversible fastening, and we ultimately chose screwing since it is reversible, serviceable, and also well understood for the torque profile. Some other things we looked into are adhesives and also nuts and bolts. We chose not to do nuts and bolts since we needed dual access on both sides in order to make sure that the bolt is secure and the nut is able to be, the bolt can be screwed and the nut is secure while the screwing is happening.
Next slide.
Now, our engineering approach includes a rigorous risk mitigation strategy. Our primary technical concern is the ML inference latency on space-rated hardware, which we are addressing through model distillation to target a sub-500 millisecond cycle. Now, to handle thermal management in vacuum, we've integrated passive heat sinks tied to the bosun's locker structure and utilized duty cycling for the compute unit. We've also neutralized potential vision errors from harsh orbital lighting by using onboard LEDs and pre-training our model on diverse lighting data. Finally, for communication risk, this system is fully autonomous once the command is issued, meaning it will safely complete its task even during a link timeout.
Next slide.
Now, looking ahead, our roadmap to a preliminary design review spans roughly 18 months. We are currently in phase 1, where we are validating our models across more than 50 different assembly scenarios in simulation. As we move into phase 2 and 3, the focus shifts to hardware integration and rigorous environmental testing, including thermal vacuum and vibration qualifications for the boson locker interface. We will include in phase 4 a full end-to-end autonomous assembly demonstration. This structured approach ensures that by the time we reach PDR, we have a flight-ready architecture that is fully compatible with our case's port requirements.
Next slide.
To start off with some of the most innovative concepts, I want to highlight some of the concepts that redefine our approach to orbital robotics. Firstly, we're leaning heavily into the sim-to-real transfer. By creating high-fidelity digital twin of the boson's locker environment, we can train our vision models entirely in simulation. This allows for zero-shot deployment, meaning we can deploy directly to flight hardware without any on-orbital retraining. This drastically slashes commissioning time and removes the bottleneck of having to collect data in space before we can start working. Additionally, we can do multi-arm cooperative assembly. We can coordinate multiple robotic arms through a single perception backbone, essentially acting like a shared brain for bimanual manipulation, allowing two arms to handle complex tasks just as naturally as a pair of human hands.
Next slide.
While some of our concepts are ambitious, we have identified some critical technology gaps that must be addressed to make this a reality. First is the lack of space qualified ML hardware. Right now, there isn't radiation hardened processors that are capable of running transformer based vision models at the speed that is required for real time, safe robotic control. Closing this gap potentially by hardening commercial edge AI chips like those from NVIDIA is important for the future of AI driven space robotics. Another hurdle is the hardware standardization. Specifically, we need standardized robotic tool change interfaces for microgravity. Currently, there is no universal quick change port designed for orbital arms. Standardizing these connections is necessary for the ISAM ecosystem, allowing for modular and serviceable spacecraft, which we all want to see.
Next slide.
Now, of course, development hasn't been without any of its challenges. So the first wall we ran into was with the compute feasibility. Early benchmarks show that inference times of 2 to 4 seconds per action, which is far too slow for dynamic orbital tasks. While we evaluated lighter alternatives, we found that the superior language grounding of the VLA architecture is what makes the complex reasoning possible. And this reinforces our priority. We need better space hardened hardware. The sim to real gap also remains a persistent challenge. Even when a model is perfect in simulation, things like lighting reflections and texture discrepancies on a physical testbed can cause issues. We've mitigated this by using domain randomization, but it is a primary risk factor as we move towards flight.
Next slide.
So to kind of wrap things up, let's take a little bit of a recap. So what we have built is a conceptual design for a fully autonomous assembly payload, specifically tailored for the Arkansas Bose's locker. By powering this with foundation vision models, we have moved away from rigid pre-programmed scripts, and now we have a system that understands and executes natural language task commands. In our demonstrations, we proved that the system could chain together 3 distinct operations: pick and place, self-piercing, riveting, and screwing. This creates a cohesive workflow where a single high-level command can trigger the entire assembly autonomously. This matters because autonomous software-driven assembly is the essential bridge to scaling ISAM, and we are building exactly this through our platform-agnostic intelligence for routine orbital manufacturing. Looking ahead, we're moving into hardware-in-the-loop testing and targeting a publication in AIAA SciTech 2027, and we are eager to explore partnerships that will help us move this technology closer towards a PDR. Thank you so much for your time. We'll take any questions now if you guys have them.
Okay, we have questions here.
This is Sarah. Did you address the data communications aspect? I was looking for it as it is part of the rubric.
Yeah, we did address the data communication handling. I believe if you guys go to slide 12, it should go over what we foresee our operation to take in terms of bandwidth wise, as well as how we foresee the entire pipeline to work.
Okay, appreciate it.
Yep.
Hey guys, really great question. One question I had for your riveting and screwing process, did you guys foresee any potential issues with unwanted cold welding? Do you guys think that limits the type of systems you can support or materials that you can work with based on that?
That is something that we still need to further look into as to what sort of conditions and environment would affect that. We mainly chose riveting and screwing because it was something that is already screwing is already used for operations in space. So it is something that we thought is a proper operation in order to perform, but we'll still need to look into how environmentals would affect those operations.
Thank you.
Yeah, hey, cool stuff, guys. So a little bit of questions relative to your chain of thought on, so natural language recognition is great. That's a human interface. It's low information that would go up. But my question is, I didn't quite see the thread between that specific activity as a user interface, and then how does the robot on board utilize the appropriate algorithms to make sure it avoids collision avoidance, navigation changes. That wasn't clear, right? It wasn't immediately there. The second question that I had is that there was a mention that this is hardware agnostic, and I was trying to understand how you can state that when different robot arms have different performance constraints keep out zones, singularities, etc.?
Yeah, good question. So talking about the second one about hardware agnostic, most of the presentation we kind of our main value or key add here was that we are actually software agnostic. If we'd mentioned hardware agnostic, that may have been like misunderstood or may have been in a different context that we were referring to. So our main key add is we are software agnostic because we do realize, and exactly what you said, the hardware that goes on different types of scenarios is obviously different. And so we cannot claim our hardware agnostic. Rather, we can claim that our software, while being with a little bit of fine tuning, can be adjusted to every single scenario theoretically. Now, in terms of your first question, kind of to explain how the pipeline works. So the VLA, what it does primarily is it takes in the camera input and outputs either one of two things, depending on which framework we're using. For our current framework, it just outputs the tool that it should use. And so, for instance, if I was to say, go and screw this grate or this panel to the yellow floor or whatever, right? Then the VLA would, since it is a kind of reasoning model, it will reason through it. And it's kind of, we already pre-built the set of tools that it has access to, kind of give it the context. And from there, it can say, okay, well, if this user needs to screw a panel to a floor, it will most likely need a screwdriver. So then we have it once again in the context that the screwdriver is the red tool, and it's already pre-built where that red tool is in its environment because that's already fixed. So after that, we just use simple algorithms and inverse, well, not simple, but we use algorithms and inverse kinematics to go from point A to point B. As well, on top of that, we do have like force sensing as well as continuous camera input to ensure that whatever we are doing is robust and is operating precisely. So a good example of this would be, for instance, in the force sensing essence, you mentioned how do we know if we hit another object or if we hit the floor. We have these bounds set inside our into our code that if a joint angle within the robot is past a certain angle, which we considered all the possible cases, then the robot will essentially treat that as an upper bound or lower bound, depending on whatever pose that the robot is currently in. And
okay, I'm gonna have to pause you there because it's been a long answer, and I know we had one more question, and I'm sure the question and answer will both be crisp. Sorry to interrupt.
Yeah, no worries.
Yeah, a quick question on tech. I like to see the addressing the technology readiness and correctly identifying microgravity, but it inferred that that was your only space-related upgrade from a terrestrial need. I would have liked to seen a conversation on the effects of vacuum and heat transfer problems and micrometeorite impacts. And if you're going to go there, technology readiness, you need to address more than just microgravity. Other than that, it was really good.
Thank you. We'll definitely take this feedback into our process next time.
Okay. Let's thank Purdue Astrobotics again.
Thank you for your time. We appreciate it.
We are on lunch break. It's going to be an extended lunch break because the first team after lunch is withdrawn. So we will be back at 1:15 Pacific, 4:15 Eastern for the final briefing of the day from MOCA from Embry-Riddle. So yeah, it's right up there on the board. You can see it. Thank you all this morning. And if you're in El Segundo, come over and join us for lunch here. All right. Thanks all. We'll see you later.
I owe you a name tag. Oh. And your name is? Jonathan? That's not George. This is.
Okay, we're gonna wait till 1:15, just 1 minute from now, but I will at least say that our next team up is the second team from Embry-Riddle in Prescott. This is the manufacturing of cold welded assemblies, or MOCA. And once that clock ticks over 1:15, you guys can get started.
Good afternoon. Welcome to Manufacturing of Cold Welded Assemblies Outbrief on Track 1. Next slide, please. I'm the team lead, Cordelia Kohuth. Presenting with me today is my co-team lead, Kimo Marquez, my mechanical lead, Manan Patel, our electronics lead, Daniel Mount, our control software lead, Ella Ozatai, and our electrical engineer, Kevin Yoon. Next slide, please. So in order to make sure we met all of the required tasks for both our Capstone class and the Cosmic Challenge, we utilized a timeline that lists kind of the main overview tasks that we needed to hit, starting with our project start and program manager selection in early September. That followed through with our trade studies being completed in mid-October, preliminary design review and finalization of CAD happening kind of between our December and January, with our prototype build and verification happening throughout most of this semester, which will culminate between this outbrief today and then our system verification review at the end of April. Next slide, please. So with the advancement of space exploration, larger structures are needed to be built in space. Next, please. So with larger structures being built, and more space missions being needed. Next. Rocket launches are increasing, so moving manufacturing to space does help reduce the number of launches needed, because it helps manage payload capacity better. Next, please. So with large structures being built in space, we can better utilize payload space by sending up raw material and then complete fabrication of an entire structure in space instead of having to build and then assemble said structure, which helps to change and update different configurations needed for different satellites. Next, please. So next. So with our the first objective MOCA plans to complete in order to help further building large structures in space is to prove the concept of using cold welding as a manufacturing technique to create joints, as cold welding doesn't require added materials and can be done without having to refuel. It just needs pressure, so you can actually just use motors. And then our second objective, next please, is repeatability. And so we want to be able to create more than one joint with our system, just so that we can actually use it more than once. Next, please.
Okay, so what does the overall concept of operations look like for MOCA? If we go ahead and tap that button one more time. So first of all, we want to launch MOCA alongside materials, either in the same launch or separate launches, depending on wherever we are in the mission. Next, we will have a rendezvous sort of operation where MOCA will link up with the raw materials in space. And then we will, next please. Then MOCA will take those raw materials and start fabricating a truss structure for whatever purpose that the client deems necessary. And then for end of life, MOCA will be deorbited and will burn up in atmosphere. All right, so taking a closer look on the third aspect of that, how are we actually going to create truss joints? Next slide. And one more, please. All right, so first of all, when we rendezvous with the raw material, we will have the raw material provided. In this case, we are designing around aluminum 3003. It's a more malleable aluminum. And then passing up to the next, we are going to remove any contaminants by scraping off any oxide that might have formed on the aluminum members between when it was launched and when it is intercepted by MOCA. And then next, please. Then we will have two of these members that have been cleaned aligned in a certain orientation to create a joint. And then with the final step, next, please. We will apply a force that will force these cleaned metallic members to bond together using cold welding. Next slide.
Yeah, so there was three main trade studies that we had that kind of directed our whole design. The first one that we're going to talk about is our pressure mechanism, how you're going to apply that pressure. So after we did that trade study, we kind of came up with two solutions. One was electrical mechanical screw and then electrical mechanical spring. Other solutions that we looked at included like solenoids and pneumatics and hydraulics and stuff like that. But we ended up choosing electromechanical screw because it was more simple than a spring, and springs also come with a lot of safety concerns, especially when there's huge amounts of force behind it. After you wind that up, there are safety concerns. So we decided to go with electromechanical screw and then pair that with a lever to amplify the force that we generate with our motor. Second, we came with our cleaning mechanism, and there we kind of had to figure out how you wanted to get rid of our oxide layer. And in the end, we came up with a solution that was actually one of the ones that we didn't actually end up picking. We ended up going with the abrasive wire brush instead of a belt sander because our mechanism already was basically a conveyor belt on the bottom that takes a sample from one end to the other. So there's no point of adding a second conveyor belt with a sander on top. So instead of adding that extra complexity, we had to have an abrasive wire brush that was stationary to make it simple. Our last one, and arguably the most important one, was our joint. Now we chose to do a lap style joint instead of a butt joint because, again, simplicity was a very huge part of our decision making. And although you can kind of do more with a butt joint in the way of angles and shapes, since we were doing a very straightforward joint, we decided to go with a lap style one. Next slide. So here is a quick stop motion animation that kind of just shows how our system goes through its ConOps. All right, next. All right, yeah, so we're going to dive into the alignment mechanism first. Next. All right, so the point of this mechanism is to take it first through the cleaning mechanism and then into the pressure mechanism. Now, here, next, first the members are then put into our carriages, both left and right. And from there, they are pushed through our cleaning mechanism and go through multiple passes until the oxide layer is removed. Next. So there's a cam also that you can kind of see with like it's a little wedge. And basically the point of that wedge is to cause an overlap of the members after they pass the cleaning mechanism. If you go to the next slide. Here is a better view of what the cam looks like. We have a bearing that basically rubs on that cam and causes cross movement. And then after it passes that cleaning, it causes that lap style joint when it enters the pressure mechanism. And the alignment mechanism is basically ran by two motors. Next. And these are two NEMA 17 servo motors that we're using to control the motors, to control the movement of the carriages. And basically, next, as they rotate clockwise, they'll go towards our pressure mechanism, counterclockwise the other way. Next. So we have two limit switches, one at the very start, which is our homing position, and then one at the very end. And that's basically to signify that we reached our pressure mechanism and we're good to start applying our pressure. Next. And then yeah, that's just an arrow signifying the direction we're going in. Next.
As for why it's important to remove the oxide layer, when you remove the oxide layer in the cleaning mechanism, it allows the two metal members to create a stronger and more clean weld. So that way, and since it's in vacuum, MOCA will then not have that oxide layer grow back, which then allows the cleaning mechanism to take advantage of the exposed metal members and begin to create that weld. Next, please. So to actually remove the oxide layer, you can see the cleaning mechanism up on the screen. Next, please. So we use abrasive wire brushes to scrape the oxide layer off of the aluminum members. Next. And the nylon cleaning brush then removes all of that scraped off oxide layer and prevents any of that debris from staying on the clean surface. Next, please.
So after the alignment mechanism brings the weld samples through the cleaning mech, it brings it over to the business end of the system, which is the pressure mechanism, the large vertical structure. Next slide, please. And here we can see a little bit of a close-up where the action actually happens is the crimper head. It's between the two vertical extrusions there. And what that contains is two pins that press down on the overlapping samples in such a way as to cause enough plastic deformation that you get diffusion, you get atomic diffusion where the metal atoms actually pass through each other, even if there's a little bit of some oxides on the surface left over. Next, please. Yes, and that's that jaw right there is where the samples actually slide into for that pressure application to happen. Next. And here is to make it a little bit clearer what's going on, a cross-sectional view of the crimp head. So there's a pin that transfers the force from the NEMA 23 motor and through the two, we got a forward threaded and a reverse threaded 3/8 lead screw there. That force those two levers apart and then concentrate that force on the ends of the two pins. And you can see the in that bottom right kind of cut out the closed position of those pins and the smaller portion, those protrusions there. That's what actually causes the plastic deformation in each of the welded samples to promote that atomic diffusion and get a good atomic bond between the metal atoms. Next slide. And for the requirement to fit within the volume of Arcus's Bosun's locker, the whole mechanism was designed to fit within the locker. And our CAD model here shows just kind of a sample of the volume requirement for the Arcus's Bosun's locker max. We do fill up pretty much that entire volume. And our physical model does match the CAD here. Next slide. And here is an example of the electrical subsystem. So on outside of the chamber, we're going to have a separate harness, and then on MOCA itself, inside the chamber, is going to have its own harness, and they're going to connect to each other through a 25-pin connector that is on a bulkhead on the vacuum chamber. And that transmits signals from two laptops, one that will be sending the control signal to one of the Arduino microcontrollers to run the motors, and a separate one that will read the signals coming from another Arduino that carries they're not depicted on here, but we have the 5 limit switches and the 6 temperature sensors that we have on each of the heat generating components, the motors and the motor drivers. And the harness also transmits the separate 28 volts, or actually, sorry, it's not 28 volts, the 24-volt power supply to actually feed the motor drivers. And on the inside of the vacuum chamber, we have been careful with our material selection. We are using vacuum compatible wire, the same kind of wire used on spacecraft, ETFE insulation with like a silver plated copper wire. Next slide.
As for MOCA's control software, MOCA will be using the I2C or the inter-integrated circuit data protocol to gather the data from the temperature sensors, the limit switches, and the motors. So that way someone can manually input those commands and initiate the commands into to initiate the cold welding process to ensure that MOCA is a semi-autonomous system. And the code that we have chosen to write was written in Arduino IDE. Next slide, please. So as Daniel mentioned previously, One laptop will be inputting that command into the serial monitor. The serial monitor will also be we'll be posting the data onto the serial monitor with the timestamps, so that way the observer can then also track what is happening in MOCA and where the system is at. Next slide.
Okay, so during our design process of creating MOCA, we explored many different innovative ideas. Next, please. The first and foremost, the biggest thing that we've designed this entire project around is using cold welding. Cold welding, typically a very annoying process that happens in space where our moving joints just start to freeze up and we can't use it anymore. But we wanted to take that process and use it for a constructive purpose. And so that's why we created MOCA. Next, please. And when we were going through different ideas for how to remove the oxide layer off of our aluminum members, we briefly discussed the use of laser cleaning. This was an interesting process that we would have loved to explore. Unfortunately, due to budget and time constraints, we were not able to implement this into our design. Next, please. We also went over some ideas about communication using lasers. This would help greatly with data transfer rates and like how we would actually communicate from ground to our to MOCA out in orbit. Unfortunately, we also could not explore this due to time and budget constraints. Next slide, please. So MOCA was designed as a demonstration of this orbital cold welding process that we could potentially use to construct space trusses. But please, next, please. But in order to create an actual product that will be widely used in space, we need to adapt our pressure mechanism to accommodate the more commonly used materials for space applications. Currently, we have designed around aluminum 3003, but if we wanted to move to a more traditional aluminum 6061, we would have to upscale our pressure mechanism in order to apply enough pressure to get the plastic deformation, force those metal atoms together in order to create the bond. Next, please. We will also need to increase the amount of degrees of freedom in our design. Currently, we are just on linear rails that has a cam that pushes the joints together into a lap-style joint. And basically, we can only create 180-degree joints here. So if we wanted to actually create massive truss structures in a chain, we would need to have more degrees of freedom. We need to angle it in various different ways. So we'd have to find some way to increase the degrees of freedom there, either using a robotic arm or some other clever solution. Next, please. And finally, in regards to the cleaning mechanism, currently, this only designed to remove the oxide layer and keep the members clean. Any particles that come off of it during that process is just floating around in the bosun's locker. So if we want to reduce this, make it so that it's not a problem, it doesn't have any risk of adding to additional space debris, we want to design a much more clever particle containment area inside of MOCA's design in order to, one, avoid adding to the extra space debris and also to prevent recontamination of our welds from floating particles. Next slide. In addition, we faced many challenges in the development of MOCA. First and foremost is the manufacturing challenges. During our design, we made many design choices that we thought would work, and it looked like it would work in the CAD, but turned out when we actually created a prototype, it did not work as we intended. For instance, with this plate depicted here, we intended to use countersunk screws to keep the plate flush with the ground. Unfortunately, the plates were not thick enough to prevents these screws from protruding through the plate and causing several stress points to form up on the bottom of our extrusions. So to fix this, we switched to button head screws and washers in order to help support that better. Next, please. We also needed to come up with a way to determine how well our cleaning mechanism worked. There's not really much data on how well one pass through through the cleaning mechanism, or like how many passes of a brush it takes to remove an oxide layer. So to solve this, we decided to mark our members using Sharpie or die-chem, and then passing it through the cleaning mechanism and seeing how much of that layer removes and how many times we would want to pass it through in order to completely clear out that area. Next, please. And finally, we wanted to find a way to determine our weld quality. Currently, we have plans to test the weld strength of our members after they have been joined together, and determine what that microstructure would look like after we've pressed down the two members together using dye penetrant testing. We want to eventually figure out a way to do non-destructive testing of our samples, and that would be very valuable for actual in-space application. That way we can rest assured that our trusses will not break when we actually create them. Next slide, please.
With the several challenges that MOCA has faced during manufacturing, there are some risks that have been predetermined by us. So this is a standard graph of a risk matrix with the consequences and the occurrence of the possibility of occurrence. As you can see, we have quite a bit of risk, some of them having an asterisk next to them because that is a critical risk. For example, motor damage is a pretty big risk in our product due to us having three motors, one for the lead screw for the pressure and two for the alignment mechanism. As you can see, we did some mitigation to these risks. For motor damage, you can see that it has gone out of the red and went into the yellow, which is still pretty, it still could occur pretty well, but it's a little lower. The mitigation we did for that was when we would degrease, or we would replace the grease in the motor, we won't completely get rid of all of the caps. We would get rid of a small amount. So when we put it back in, nothing significantly changed. And we would also pre-bake it, so there is no damage to the motor. Next slide, please. Due to the prototype being near to being finalized, we will perform thorough testing to be able to get to the preparation for the PDR. We, as a team, we've come up with 8 or 9 verification plans, and we are going through most of the verification plans recently. Major ones that we've recently done is the metric sizing. So we wanted to make sure it could fit in the bosun locker, and the weight sizing or weight measurement. And we also would like to run the code, make sure the code runs properly. Next slide, please. And for major missions that we want MOCA to run through, for example, we want to be able to help NASA's a small satellite factory. We would like to give them another option other than nuts and bolts. We would like to be able to send our project up into space and help them out with the creation of satellites. Next slide. And if you guys would like to have more details about our project, we did create a paper with a 230-word abstract. It's 10 pages, 2 references, and we are proposing to publish this at AIAA SciTech Fest. Next slide.
In conclusion, MOCA plans to help enable the construction of cold welded truss joints while in orbit. Next, please. Thank you. Are there any questions?
Okay, are there any questions from the judges in here? Okay.
And I got one.
Go ahead. Go ahead.
Jacob, this is Andy. So some pretty impressive hardware. Did you guys design it and build it yourself, or did you get help?
So Embry-Riddle does have machinists on staff that did help us do the manufacturing. We did design all of the CAD parts ourselves. We purchased the extrusion, it's 4040 extrusion. But all of the other parts we did design and we did have some help manufacturing with those from the machinists on staff.
So you actually build the CAD files to come up with a configuration and just sent it out to have them, and everything fit together first time?
There were a couple minor issues, like we had, other than the plates, as we mentioned earlier with the countersink not being correct. We did run into some issues with some purchased parts that we had, like our wire brushes didn't match the CAD file that we found for them.
Hmm.
And so we did have to make some minor adjustments to our cleaning mechanism for those to fit properly and securely. But the majority of the parts that we hand designed, like the pressure mechanism, those all fit together just fine.
Okay, good. Thank you.
Hey guys, great presentation again. One question I had for your clamping process. Do you guys think that there will be some oxide layer that might be needed on the two clampers to help or to ensure that they don't get cold welded to the materials that you're trying to clamp or cold weld?
Yeah, the main thing that we're using there is we're building those out of dissimilar materials. So the actual crimping dies themselves are made out of a tool steel. I think we used A6. So those were machined and done separately. I did do a quick run through, not using the code or the NEMA 23, but I used an electric drill to run the pressure mechanism down, and still actually got much greater adhesion to the crimp dies themselves. They probably need to be polished, and that was not in a vacuum where cold welding would have been a concern. So there are still challenges with making sure that the adhesion forces between the metal samples is greater than the adhesion forces to the crimp die. But the main reason that the main way that we solve that problem is choosing dissimilar materials that won't be likely to weld together.
I have a question, and you know, cleaning the surface, as you guys noted, it creates debris. You're in the boss's locker, so you kind of mitigate it there, right? What do you do when you're out in space? Like how do you clean that part? How do you clean those surfaces?
So one of the ways we were thinking of doing that is adjusting the cleaning mechanism to potentially use something that is more like a laser, so that it creates much smaller particles that are less of a concern. The other option, in addition to also building a containment mechanism, like something that allows for containment of those particles so that they don't end up flying around, so that the cleaning mechanism is contained, and then the cleaned material gets passed out of the cleaning mechanism into the pressure mechanism.
So and I can see your gears turning as you're talking through that answer. Is I'm famous for I hate solutions that create more problems than they solve, and so you know like that's right. If you create debris, now we have to contain it, so we build a container around the debris, and you're really clever mechanism of joining these things and taking advantage of the vacuum of space. Now you've created a new problem to solve. So I would encourage you to think about like, okay, you know, like you said, like, well, create debris small enough that we don't care about it, or find a way to do it without creating loose debris, right? I mean, I don't have an answer. But yeah, it's good to work through those problems, because you kind of go along and you realize, oh, this is a problem. Do I have a solution, or do I go around it? Any other questions online or in the room?
First of all, great presentation. That was very interesting. Second of all, is there any plans to reduce the amount of computers needed to run the system?
So all of the code can actually be run from one computer as long as it has 2 USB ports. So the Arduinos just need 2 separate connecting cables right now. You theoretically can wire the 2 Arduinos together so they pass signal between the 2, but we did want to be able to run the code separately for testing purposes.
All right, and we are at time, so let's thank MOCA again. If you're online, if the judges can complete your scores and submit those, if you're in the room here, don't go anywhere. We're going to get together for a photo before we go on the tour, and we will be back tomorrow morning at 8 a.m. Pacific, 11 a.m. Eastern, 6 a.m. Hawaiian Standard Time, and And yeah, we'll see you then. Thanks all. Thanks for a great first day, and we're just getting started.